Miguel Vallejo or team. I know Miguel is one of our alumni, and I know him since around 2014 or 2013, I guess. Since 12 or 13 years. Let me introduce him briefly. Miguel holds a bachelor in forest engineering in Spain. Thank you. And as well, afterwards, a master in geoinformatics and photogrammetry at our university in 2015. He continued his academic research and finished his PhD at the Heidelberg University 2 years ago in 2023. In addition, what I did not know so far, he holds also a master in data science at Universidad Complutense de Madrid. After holding various positions in public and private institutions in Spain and Germany between 2009 and 2016, Miguel served as a lecturer at the Namibia University of Science and Technology from 2016 to 2023, quite recently. And there he organized one of the AGSE conferences, or co-organized one of the AGSE conferences. There, his research was focused on monitoring gully erosion using remote sensing and GIS. And starting in 2024, he worked as a forest engineer, specialized in forest plantation for energy production and climate change mitigation. Currently, he's working as a researcher at the Spanish National Research Council, contributing to projects in hydrology and watershed management. You can already see the topic, and it's a very important topic about the contribution of Earth observation. And now the floor is yours.
Thank you very much. Good morning, everybody, and thank you, Prof, for the introduction. It's really my pleasure to be here today and to talk about this topic. And of course, first of all, I would like to thank you to the organizers from the German side and also from the local side for making this happening. So, the topic today is about climate change monitoring and how, in our field, how we can contribute from the Earth observation and remote sensing side, basically to monitor what is going on and understand better the different processes, and basically to plan the future and to also support with data the climate projections which are currently going on and being in process, calculated. So this is the outline. We will start introducing little bit the current state of the climate change in the Earth. We'll review a little bit the different Earth observation for climate change technologies, moving to the legal framework and how science for policy and Earth observation can help to support policy making, finishing to emerging trends in Earth observation and current and future challenge in the field. So, as you know well, climate change is already a fact. It's changing our world, although historical records demonstrate that it has been happening throughout the time. But currently, there is a clear evidence of warning, and the acceleration is much higher as compared to the last 10,000 years. And it's also a clear proof from the scientific community that the human activities is the main trigger of this change. So basically, it's very important to support all this process to increase the understanding with Earth observation data. But let's see some evidence of this climate change. The first and the most evident or the most impacting one is the change in the temperature. So the Earth is warming, and the pace of this warming is being accelerated. It's proof that since the industrial era, the industrial time, there is an increase of 1.5 degrees in the average temperature of the Earth, and which is caused by mainly human activity from emission of fossil fuels, massive deforestation, and the release of greenhouse gases from industrial activities. Of course, it influences many aspects of life, from technology of animals and plants, and also the viability of agriculture. And in terms of human security, it also affects heavily. For example, we are more impacted by droughts and extreme climate events. It also affected the ocean, because the ocean, the water of the ocean is absorbing much of this heat, and it's also getting warm in a rate of, or in a magnitude of 0.33 degrees Celsius since the 60s, And this is very important, this warming, not only because it affects, again, the biology of plants and animals and life species, because it also pushes the water to expand. It's also one of the reasons why the water is rising in the oceans. And this is obviously the next slide, talking about the rate of this rise, about 20 centimeters in the last century, not only derived from the warming of the water, but also from the melting ice and the snow areas. But it's important to highlight that this rise is accelerating in the last 2 centuries, in the last 2 decades, sorry. So we can see, again, in these maps how there is a different distribution of these effects, but each of them is happening in a different area most heavily. For example, the warming of the ocean is happening in the intertropical area, and the rise of the sea level is happening mostly in areas which are close to this ice at the poles and ice parts of the frozen parts of the Earth. So also the glaciers and the ice frozen parts are retreating. For example, in Greenland, in a rate of with an amount of 279 billion of tons of ice in the last 20-25 years. In Antarctica, it's a bit less, but also massive numbers, 148 million of tons of ice per year. And glaciers are also retreating around the world, in all the continents. There are a lot of studies in the Alps, in Spain, in America, Alaska, and even in Africa, proving with maps and with scientific research that there is these glaciers are shrinking, they are retreating. And just to mention, the last evidence is the increase in the frequency of extreme events. So the number of records since the 90s are increasing when these extreme events are related to high temperature events. They are decreasing the low temperature events and increasing the rainfall events in the Earth. Sorry. You can also see in these graphs how this fraction, these proportions, are more evident in the meteorological, climatological, and hydrological events as compared to the physical events, which are more or less stable. So what's happening, more or less, is that there is a distribution of probability of occurrence of extreme event, And so the winds are the winds of the normal distribution are the extremes. So the distribution is more or less the same, but it's shifting towards the hot part. So the extremes on the right wing affected by high temperature events are more frequent and higher. That's a very brief summary of what's happening with the weather and the climate change in terms of extreme events. So what's the state of the art? So basically we understand more or less through historical records and ice core data what has happened in the past, but the real challenge is to understand or to try to predict what's going to happen. And for this data, it's very important to support the decisions and to understand the different process, where of course geoinformatics and Earth observation plays a significant role. So these models are built under the umbrella of the IPCC, Intergovernmental Panel of Climate Change, which basically takes care of the state of climate, delivering or producing reports frequently every second or third year. And the last one was released in 2023, which already some confirmation of climate change in every region, and but giving some hope. Basically with some guidelines in terms of the reductions in the emissions, in the greenhouse emissions, can actually slow down this climate change effect, but it must be maintained in long cycles at least 20 or 30 years. They also give recommendations for climate policies, and they create narratives, which are called the shared socioeconomical pathways, which basically develop scenarios of climate change from very positive or optimistic one to the very pessimistic, where the fossil fuel development is basically in place. So according to this, there are some projections for the content of CO2 in the atmosphere, some models taking care of this, let's say, prediction of the future. And again, for this, the use of data is very important, because it really makes a bridge, Earth observation, between simulation and reality. So talking about some of these models, we can see, there is in place this CMIP6 project, which is coupled model of intercomparison project, which is the umbrella. It sets protocols for experiments, models, and time periods for projection or prediction models. So what we see on the right is a figure of the different, or some models making a projection for the increment of the temperature. Some things to comment here is they are linked to different labs belonging to countries, although there are some consortiums, for example, at the European Union and the European Commission. But it really, I would like to highlight the huge variability in the projections. We can see by the end of the century, these predictions for a specific scenario is really, the difference are more than 10 degrees. So there is a huge uncertainty in this type of projections. That's why a process of validation of this data and this calibration is very important. So why they are so different? What is where comes this difference in terms of calculation and results? First, because there are two groups. First, only climate models based only on physical climate process, and then those which are the Earth system models, more complex, taking into account the human activity and the feedback between the atmosphere process and what the humans are doing with basically in terms of management of forest and emissions and the aerosols, emissions, and so on. So again, as I mentioned before, Earth observation is the bridge between the simulation and reality. In order to validate these models, we need Earth observation as a key component. And that's why we are going to talk a little bit which is the state of the art and a bit of history of the use of Earth observation for climate change. So first, by definition, I think most of us very familiar with the term, but Earth observation is the process of gathering information in the Earth by a ground-based, airborne, or satellite remote sensing platforms. While remote sensing is almost the same, they are overlapping, but from the distance and usually measuring the reflection or emitted radiation for management in any setting, but especially in urban settings, yeah. Type of information with human health and urban planning, and also biodiversity within cities and so on. But as I mentioned before, most of these products are available in platforms like this one, the NASA World View, where we can access to most of this data. Like here we have inner water bodies, the time series of inner water bodies, so we can download and access this type of layers, many layers that derive from climatic or useful for climatic monitoring assessment. So I motivate you to explore these tools if you don't know them. I'm sure most of you know, as well as the Copernicus Change service, which offers also some climate projections. Here is not only about the past, we can also browse and use here reclassified data for most of the climatic variables which are produced for the models I presented at the beginning. So we can see under different scenarios how the climate is going to change through the different parameters and variables until the end of the century. So it's very intuitive, and as I said, they are ended products available for the public and open and free. We can also get to these tools through, for example, the API of each service. Like here, I just pasted an example of how to access the Sentinel Hub from Python, which is very easy and intuitive. You just need to basically enter your credentials of the API service and then make a query to retrieve the data you actually need. Very interesting and very important to embed this type of codes in automatic pipelines, which can be even linked to real-time monitoring. Yeah. So this is probably the way forward, as well as computing in the cloud. A very popular tool is also Google Earth Engine. And again, I have here as a showcase how we can access data from, again, these climatic models and for variable projections. And yeah, so it's again very intuitive. It's coded in JavaScript, and you can query the time, the model. Here we have the AGSE CM2, which is the Australian model, the scenario, the most positive itinerary or narrative, the green way, and the parameter or the variable we want to retrieve, and yeah, simple as that. So again, computing in the cloud is the easiest way and probably the most efficient when we want to conduct global studies. But of course, when we study climatic variables, we cannot consider a static event, because it's a trend. Yeah, it's a sequence of events or sequence of observations which really defines the climate. So we have to work with time series. Time series are observations collected at regular times, which really helps to understand the behavior of a system, of a dynamic system like the climate. It has different components, so a time series can be decomposed into trends, the general trend, the seasonality, the small, like winter or summer, or rainy and wet season, the cycles, which are like, for example, the daily cycles, and compute correlations to understand the relations of these trends with other factors like human activities. Yeah. So the idea, once we can describe a time series, to forecast the future behavior. For this, there are different classical approaches. The simplest one is just a linear regression. We fit a linear regression to see what is the general trend of a specific time series. If we want to capture changes, it's probably most appropriated the use of nonlinear trends to capture a specific pattern in terms of a change, like a sudden change or up and down. There are a huge collection of trends which can be modeled mathematically. If we want to forecast the future, another traditional approach, again, relying on statistical methods, a single exponential smoothing, which basically relies or assigns weights more to the recent observations and is useful for short-term forecast. Yeah. If we're going to have something a bit more sophisticated for a longer trend, we can use the hot winter method, but there are plenty of methods like this. This one is a bit more complex than the previous one because it takes into account the trend and seasonality. So it basically can model the future, taking into account recurring patterns, for example, the cycle of the plants, yeah, in terms of when there's the growing or the blooming period and so on, which is more or less fixed every year. And of course, recently or in the last 10 years, let's say, machine learning also played a very significant role for forecasting and for analyzing time series. It's a significant advantage because it can capture very complex patterns and relationships, reducing the manual or the human intervention and decision in the process, and it's also able to capture anomalies and to generate classifications and to generate clusterings and also to make predictions. Just to mention two algorithms that are widely used. The first one, time series forest, is like a random forest for time series. It extracts features of the time series, for example, the slope, maximum, minimum, but it can also extract a curvature, any feature that the researcher finds interesting, and makes the classification or describe a time series according to these features of extracted by the moving windows, and you can find actually patterns in another series. So it's very useful, for example, when it's extreme climatic event, you have time series, you capture or you describe through features this time series, and you can find these patterns somewhere else, maybe to predict a very extreme event. And very popular, recurrent neural networks. I'm sure, again, you are familiar with it. Probably more than me, but anyway, it's based on inputs and neurons which are connected to each other, able to capture the patterns or relationship of the data and to keep memory. So it's not only the static present relationship, also keeps the memory of what has happened in the past in order to make a classification or a future prediction. Again, so this is just a few examples how to process and manipulate the time series in the context of climate change. But now that we made a review of technologies and some techniques and so on, probably one of the hot points is how Earth observation can actually help to support policies related to climate change once we have available all the data and all the technology, and that's why we will review a little bit the legal framework in climate change and how Earth observation can actually support this legal or the implementation of these regulations. Yeah. So here you can find a map, a bit complex and dense, about the legal framework related to climate change in the Earth. In the world. So on the left, you have the timeline starting from the United Nations Framework Convention of Climate Change in 1992 until the current COPs happening every year or every second year. And most of these frameworks are agreements, yeah, between countries and between institutions, big institutions, just to reduce emissions or to find good practice and to avoid bad practice which are affecting climate change. You can also see that each country or each region, at least the big actors, they also have their own policies, but we are not really going to get deeply into each of them. But what is important to understand is to implement these policies is really require science and data to verify that these policies, the goals of these policies are actually achieved, and to quantify, yeah, to make a quantification of the achievements and the progress. That's why in many institutions they already have an agenda for many countries, research institutions. They have this agenda for science for policy. So they really direct a lot of teams and departments to make science directly directed to support policies, national policies, but also regional policies like some of those I mentioned before, or European ones in case of Spain and Europe. In this center called the Knowledge Center of Earth Observation, which is specifically intended to find policy needs in terms of data and technology. So they work under the principle of fit for purpose. It's clear that Earth observation platforms are essential ingredient for evidence-based policy making. But how to select the data? Which is the most suitable data set? Which policy requires which type of data? So here I will give you just one example, because the idea seems a bit abstract. You read everywhere science for policy, but what is really science for policy about? What these type of teams are actually doing? 5 minutes? Okay, maybe 10. Okay, yeah, here we have one example. There is some objective for one policy, which is the Common Agricultural Policy, and they define service requirements, like in order to achieve these objectives, it's required vegetation, to have a continuous and consistent vegetation biophysical parameters. But what are the data requirements? Basically, they set specific numbers for their spatial resolution, the temporal resolution, and the type of information which wants to be extracted, and how is this information going to be extracted. Yeah, they recommend, for example, expansion missions like those that I mentioned before, but also the integration of local knowledge, like citizen science from farmers working in the field with satellites in order to downscale the observation coming from the satellites. So, coming to one of the last two sections, which are the emerging trends in Earth observation. I have listed 3 of them. The first one I think was already tackled, of course, real-time Earth monitoring, where these nanosatellites and new constellations play a very important role in combination with artificial intelligence and cloud pipelines like Amazon Web Service and Microsoft Planetary Computer, but I really want to focus more in geospatial artificial intelligence and federated artificial intelligence. Yeah? These 2 concepts, I think they are really on the hot spot nowadays, so let's try to introduce them a little bit and understand these concepts. So the first one, artificial intelligence. I know there is a very interesting talk tomorrow about GeoI, so I hope this is just an introduction, but by name, by terminology, it's just the sum of artificial intelligence and GIS, or Geoinformation technology. While I was preparing this presentation, I was just doing some research, and I found a package in Python which is called GeoI. And I discovered, I was surprised, because it was a summary of different packages or different tools which were already in place for visualization, for machine learning, for deep learning. So I wonder what is new here. Does GeoI is just the unification? Is it gathering all the tools which are already in place, or there is something else behind? So I guess the concept, after reading some paper, is a bit different. It really intends to answer questions like, okay, we have a 3D model or a 4D model of a town. How this model will change if we implement a specific policy, or if a new political party comes into place. Yeah, so it should be generative. The same way we ask ChatGPT, tell me what will happen if, and we just deliver or give the system a scenario, the same but with data. So, yes, so I think that would be the idea of GeoI, but for sure, I'm sure tomorrow, I'm very curious about the presentation from Professor Schroeder, and it will expand on this idea. And very interesting topic is the federated learning. So one of the big issues of artificial intelligence is the privacy, and that it does not account for indigenous knowledge, yeah, fairly. So this idea basically considers the participation of different actors, but not providing the raw data, but training models from a decentralized institution or device. Yeah? So the contribution is not the data, the contribution is the mathematical update of a specific model. So in a way that we can train a model from Africa, Europe, and South America, for example, and each institution or each center produce a trained model which aggregates into a centralized one. In ideal world, the final user could choose which model or which components of the model could be used, yeah, to deliver the results or to make the deep learning or machine learning predictions or calculations. In this context, of course, citizen science is also very important because it can really fill the gaps of authoritative data, and it's real-time and hyperlocal. It empowers the communities and fosters science diplomacy, and artificial intelligence models become more unbiased. Yeah. So just to finalize, I'm in the final part, 5 minutes. Yeah. So which are the current challenges of Earth observation and the future ones? One is a classical one, but I believe still in place. There is a need to balance data and resolution. It's of course a classical controversy, and it's very difficult to balance because if we want a lot of detail, the products are they are less available worldwide or for a larger extent, and also become more expensive, and vice versa. Here is just one example of the project where I'm currently working, where we work at different dimensions. First, we try to monitor through satellites change in river networks. Then, when we detect an area of high activity, we use a drone or drones just to see which are the changes in the granulometric, the rock composition. And we also have cross sections of the rivers where we have seismometers to trace specific movements of rocks. So we must more or less control the different system, but what is the implication? What is the up and down or top down travel of the data? This is the real challenge. Yeah? And another one, or different ones, are related to artificial intelligence. We already mentioned some of them. For example, the lack of transparency and reliability on the data, the lack of indigenous knowledge, some ethical considerations related to the privacy of the data. Yeah, so this is a big topic, of course, which can be somehow solved through scientific diplomacy. I believe this is also a challenge, the fact that scientific diplomacy is a bit ambiguous term. Sometimes they consider diplomacy for science, sometimes science for diplomacy, or science in diplomacy. But I guess the fact that researchers adopt diplomatic practices to set or to achieve some objectives related to those that I mentioned before, like data fusion, artificial intelligence fairness, or the inclusion of indigenous knowledge, are the way forward in terms of scientific diplomacy. There are some events which are obviously in this direction, like the big conference, where there are big gatherings of researchers, where the goal is more to create a network and to create common grounds more than go very, very deep into a specific paper or specific project. And events like this, which maintains community for 20 or 30 years, are also important in these terms, because it creates community and unify ways of doing things, as well as consortiums of data and data standardization. And some papers which try to avoid disciplinary fragmentation and really unify terminologies and practice for a specific in a specific topic. And I would like to finish just the last 2 slides, tackling the time of the limit of data sharing. So does scientific diplomacy means that everybody should share their own data from their own countries? This is an example of a working place in Spain, where this archaeological site where they do a lot of paleontological discoveries. I'm sure they will not allow other parties, other countries to go there and extract their data, because it's of course a heritage, a national heritage, but also scientific national heritage. While we have seen this in the past, in the colonial time, probably more for material, but the question is happening now with data to feed the artificial intelligence models. We have to take care of this. Some countries more than are taking advantage of others. Yeah, these are just open questions which are covered in some papers, which I'm not going to go deep into them, but I think there are again some questions like interesting ones related to this the concept of neocolonialism in science. Yeah, so sometimes the donors might there's an equal balance in the decision making while doing science. Are are the local partners just passive recipients of funds, or they are real protagonists of the research? They have this power of decision, or still the whole hierarchies are in place in the science system, science production system? And just the last one, most of these studies also highlight the need for indigenous knowledge in this artificial intelligence and interaction in science. Sometimes for spatial studies, and for example, this paper states that artificial intelligence perpetuates the spatial dynamics of the pre-colonial era, and and again, these are just open questions which are good points for discussion, and until here, so thank you very much for your attention.
Thank you, Miguel, for this well prepared and also somehow critical keynote talk. I am really impressed. We should have like 120 minutes at least for this topic, which was so broad. Okay. Thank you again. I think we should take time for 3 questions, perhaps. Perhaps time for 3 questions, short questions. Yes, please.
You can hear me well, right?
Yes. What's this one?
Okay. Thank you.
So take this one.
Thank you so much for your presentation. It was very, very interesting. Several tools for different branches inside geoinformatic topics. But there is one I'm really curious, and it is GeoAI library. Have you used it? And can you maybe, if you have used this, you can show something or explain an example where in which site you use it or something?
I didn't use deeply. Of course, I have checked the tools and the codes and so on. But I think, as I mentioned during the talk, the first impression is that it really unifies different machine learning visualization tools. So everything was more or less familiar to me. I didn't use with my own data, but there's a talk, I think it's tomorrow or the day after tomorrow, from Professor Röder, and he's going to spend 40 minutes about that. But no, I'm not an expert. I just know the basics, and so.
Okay, thank you.
Thank you. Next question.
Go to the slide number 8, okay, 9, sorry.
9. Okay.
Let's go. Okay. Something. My question is that something in your side you have considered you are going to compute the climate model. Yeah. Climate model.
This one?
Yeah. Coupled model, coupled model intercomparison. How the model is working? Can you come up?
Yeah, I mean, that's a very good question. Thank you. They account for the recent past. So we are in 2025. Yeah. So they look at the 30 years before 2025, which is, let's say, like the training period, and then they make the projections according to what they achieve in this period. Yeah. So they take a lot of different type of data from. I mean, all the models are different. That's why they deliver different results. But the input ingredients are different from atmospheric dynamics and so on. And the projections they deliver are actually quite related to the techniques I presented of time series. Yeah, a bit more complex or a combination of all of them. But they build the model with the last 30 years, and then they make the projections accordingly. And then they validate or refine the models with the last 30 years. And yeah, but the calculations, if you are actually asking about the calculations, they are related to time series and forecasting calculations. So some of them they use ARIMA techniques. Some of them, I believe, they are already implementing the long short memory networks, the recurrent neural networks. Yeah, they are different, and they are continuous improvement of the calculation methods.
Like what would be the parameters? Like something for what would be the parameters that those could be used for modeling this type of project?
What do you mean the parameters?
Parameters like what were the conditions that you would consider? What are the prerequisites? What are the requirements for this model.
But prerequisites for,
Yeah.
I think it's a fitting algorithm. So you have data from the past, you have ingredients, yeah, and then you make a model, like a forecasting model, and then the one which fits better to your past is the one which is used to predict the future. Now, if you are really asking of the details of each model, I really don't know, you know. But I know in general terms, but I don't know.
One final question by Caleb.
Just, did you, by any chance, for when you consider, there's a lot of models, and we have to use many models, right?
Yeah.
Considering which model has been more predominantly used, or it depends on the area, on the level of use, and maybe to also add to I don't know what he was asking, but if he's asking, are you talking about the variables that the variables are just normal temperature, precipitation, and so on? I don't understand what you were trying to ask as well, so I wasn't sure exactly your question. But anyway, just I wanted to know, did you have predominantly model used? Have you discovered this?
I think, yeah, some of the models are, it's okay, thank you. Some of the models have a spatial focus. So the Americans, they prefer to use the model because somehow they work like the coordinate systems. They fit better to the area. But I think the common ground or the usual practice is to filter statistically the extremes. So you take a bunch of models, 15, 20 models, and then you take out the extremes for a specific parameter, or you make an ensemble of them just to take the average, or you filter statistically those which are less significant, yeah, or the outliers. I think both are common practices. Or some of the models are also topic focus, yeah, like temperature or pollution or whatever parameter, you know.
Okay, thank you.
Okay, thank you for the questions.
We have to stop. As a small abbreviation, acknowledgement from our university, from the alma mater, the University of Stuttgart. Thank you very much. I was really impressed.
Thank you.
I hand over to the session chair, my colleague, Professor Dietrich Schröder, for the next session.
Yeah, good morning also from my side. It's a pleasure for me to share this first technical session this morning entitled Climate Change Monitoring Through Remote Sensing, Imagery and Processing. And we have 3 presentations again in this session. So let me start with just introducing our first presenter, Mr. Karupusamy Sudalai-Muthu from India. Dr. Karupusamy Sudalai-Muthu is an associate professor in the Department of Civil Engineering at the Institute of Science and Technology in Kanchipuram, which over 20 years of academic and industry experience in the field of geoinformatics. He began his career in geospatial industry roles in different companies, where he specialized in photogrammetry, mapping, and geospatial solutions. Transitioning to academia, he served as a faculty member of Anna University in Tirunelveli, where I remember I visited him a long time ago, contributing to teaching, research, and program development in geoinformatics. Since 2018, he has been in the institute, actively engaged in teaching, research, supervision, and institutional development activities. He holds a BA in geoinformatics from Anna University in Chennai, and a master degree in photogrammetry and geoinformatics from Stuttgart University of Applied Sciences, and a PhD in geoinformatics from Anna University in Chennai again. So, the slides we can see. So please, the floor is yours.
Good morning, everyone present here. Thank you, Professor, for the introduction. And today, these topics comes under the category of climate change. That's what Dr. Miguel have given the presentation about climate change. And let me start with the climate change and how it influences the agricultural crop yield. That's what my research, actually this research is done by my scholar, and we are working about how the climate change, how the land surface temperature influences the agricultural crop yield. So that is the basic idea behind that. So, so I have to add my scholar name also here. His name is Karthik Karnagaran. With this, I will start now. So these are the topics I am going to cover today, in which general introduction and objective of the study, what we have carried out, and study area from Tamil Nadu, where I am residing, and what are the materials or data we have used for the study, and methodology adopted as per the study concern, and the results what we obtained, and then the current scenario, the many research including the machine learning techniques, that also we incorporated for study. And eventually results were validated with ground data or some existing information from reliable data sources, and finally conclusion and references. So this all about the presentation consists of. So introductions, when Miguel talk about climate change, so there are 2 points about the climate change which is influencing various domain or various environmental domain. Because of that, United Nations framework for conventional climate change, it was established in 1988 in order to reduce the carbon emissions, and there are various protocols were developed, but however, what is the progress should be monitored by the UN nations. As per the NASA, they are saying that 2 degrees Celsius increases compared to globally 2 degrees Celsius, it is huge from the year 1800. And the same thing, this is intergovernmental climate change is talking about the year 2011 to 2020, there's a sharp changes in climate change, I mean the temperatures. So the temperature is keep on increasing due to the human activities or rapid urbanization, industrializations. So main point is human activities. That is the main point as far as the global outcome, the climate change or temperature increases, the human activity is a major concern. So when you talk about that, so the precipitation pattern is differs due to the climate change. That means in India, we are when I was young, we have a consistent rainfall, and every the rainfall is very consistent. We don't face any problem, especially the agricultural activity or agricultural cultivation. But the current scenario, we don't have such a thing. Actually, the rainfall is totally unpredicted. We don't know when the rainfall comes. It is unexpectedly more rainfall in a certain time that leads to like urban flood. 2015 urban flash flood in Chennai, where I was living currently, that fully submerged the whole Chennai cities. Even my college was fully covered with flood water actually. So this is due to unexpected climate change that leads to unexpected flood. So that also affects the agricultural productivity. So that is the main intention for us, that okay, we should choose this study for our research. How the climate, especially the temperature, influences the agricultural crop yield, because as per the India concern, 42% of workforce rely on agricultural activity, 18% GDP based on agricultural activity. So because of that, we choose this topic. And when we talk about the objective, the first thing is with the help of remote sensing technology, we like to identify spatio-temporal variation in land surface temperature in the study area. And the second thing is When you talk about the land surface temperature, of course, it influences the crop directly. How it is, it gives the stress to the water as well as the heat. The both things affects the evapotranspiration, which is very important as per the agriculture concern, and phenology of the plant as well as stomatal closure. Stomatal closure, which is nothing but the stomatal should be open in the plant so that cools the canopy. When the LST is high, the stomatal closure will happen. That will not close the. That means that it closes the canopy. So there is a chance for increasing the LST. So because of that, how the other parameters are influencing the land surface temperature, that is the second objective. The third objective, since many research use the machine learning models, we also thought of using some of the models, which is more for a classification, or some models, for instance, random forest for agricultural crop predictions, that is working for both the linear and non-linear data sources. So these are the main aspects. So we start with how the surface temporal variation in land surface temperature, and how the land surface temperature with various other additional parameters in addition to the parameter what you talk about, land use classes, meteorological parameter that we discussed, and finally some of the machine learning models for the study. And the study area, this is the, I would say that a rice bowl for Tamil Nadu. So many agricultural activities are happen this area, but in the current scenario, many industries are for the development purpose. There are many industries, for instance, sugar industries, textile industries, but somehow it is influencing the agricultural productivity in this area. The yield comparatively it is keep on reducing. That is the statistics. I don't know the number current now. So this is a study area we took. Many times the land surface temperature deals with urban heat island, but we thought of how the land surface temperature influences the agricultural yield. So that's what we just divert from, instead of working on urban heat island, we just divert to the agricultural activity. This is the study area. This is many heritage monuments also there in this study area. Also in addition to this agricultural productivity as per the study area concern. And there are various data sources we have used as per the study concern. We carry out the study in two different time. One is how we call like Kharif, Rafi and Zaid. These are different monsoon for agricultural activity. As far as our terminology in Tamil, we used to call Kuruvai and Samba. This is Kuruvai means it is from June to September, and Samba it is from August to January or February. The Kuruvai is only for 60 to 90 days, but the Samba is for 120 days to 150 days. But when I was young, even I am from agricultural family, we used to have this agricultural activity for every, like we yearly 3 times we do productions, agriculture production, especially crop. But nowadays, even in a year, 1 time is also not possible actually. So we are 7 from my family. Now my mother is taking care of agriculture. She is 82. She is doing only for her happiness, but yield is not that much. Only the intermediate people, they are gaining much yield from that. So as a farmer, we are not getting much money of that. So because of that, we are diverting from agriculture to other areas. Because of that, I study and something like that. So in this study, we used, these are the data sources from Landsat data, Landsat 7, 5 and Landsat 8 also used, and some of the data we derived from the meteorological department because we include the rainfall data also, and some statistical department, they provide the data for the quantum of crop yield in a particular area and particular region and particular time yield. That we also collected this data because this is a reliable data. The government produced data, so this is needed for the validation purpose. And finally, for validation field validations, we use GPS also. And these are the material we have used so far for the study. And when you talk about methodology, this, as I mentioned, these are the various data sources. and different time period. And here actually, since we use some machine learning models, we classified into independent variable and dependent variable, and finally what the output is crop yield. So for that we use rainfall and other additional parameter like bare soil index and normalized difference vegetation index, normalized difference water index, and land use land cover. These are the different data we are used for the study. Because as I mentioned, of course the temperature influencing the crop yield, it is not only sufficient for land use surface temperature alone to predict the crop yield. There are other parameters. If you include the study may enhance. Considering that, we included other parameters also as per the study consents. And we compare the outcome of machine learning model with statistical data as well as the field data. This is what the whole methodology as per the study consent. And so let me start with the methodology. We start with estimating the land surface temperature from Landsat data. Of course, as per the Landsat data consent, Landsat 5 the different approach and Landsat 8 a different approach. So of course we calculate the convert digital number to atmospheric radiance, that is the first step, and then the second step we convert the atmospheric radiance to brightness or temperatures. This is the second step. Of course we suppose to have the emissivity, that is important. As per the Landsat 8 consent, we calculate the emissivity also, because with the reference to lands classes, the emissivity will be different. So emissivity will be vary. So considering that, we have to calculate the emissivity corrections or emissivity in order to have a better results as per the land surface temperature consent. So Landsat 5 and 7 different approach. Of course Landsat emissivity is important, and but the calculation part is different. But nowadays this land surface temperature can be extract from Google Earth engine, so that is easy. That works nicely also, but this is approach followed by my scholar. And so once the land surface temperature completed, of course this is not necessary you have to follow the same order, but just for the presentation I kept it like that. And land use land cover. So I have shown different data sources for Kuru and Samba's season. We calculate the land use land cover for all the area. The basic behind that, we collect the training samples from the field. We collect nearly 50 training samples with the help of GPS as a training samples, and we feed into the Landsat image and NV 5.2 software. And with the help of these training samples, the classification was carried out. And finally, validation was done with the help of field data collected. And we have different 5 classes as per the study area consent. So the agriculture is the prominent one, and build-up area, and forestry, and wasteland, and water body. So based on the major consent, we classified into these 5 classes as per the study area consent. And as I mentioned earlier, it's not only the land surface temperature, other parameter also, additional parameter also one of the important aspect. So considering that, we include rainfall. So Indian Meteorological Department provides rainfall data, and bare soil index, that is very important. If the soil is dry, that means the land surface temperature is high. So that directly correlation with that land surface temperature and bare soil index. And in general, if you have in agricultural land, bare soil index is good. But if the land is excessive heat, then the soil will be moisture will not be there. And NDVI, normalized difference vegetation index, that is also one of the important parameters, so directly correlate with the yield, and normalized difference moisture index. And these are the various indices we incorporated as per the study consent in order to have a better outcome. And this is the formula for calculating them. And as far as bare soil index, blue band, near infrared band, and red band, and short wave infrared band. Of course, short wave infrared band can be used for other purpose also. For example, mineral exploration, we can use short wave infrared band. And normalized difference moisture index. Of course, moisture is one of the important parameters, how it can useful for increasing the productivity. So these are about the additional parameters what you included for that. And machine learning, why we choose 3? Of course, we can start with only one, but we thought of having a different combination, which one is working better. That is the intention. There may be many artificial intelligence models. For example, you have a depth breadth search and like breadth width search. There are many model, genetic algorithm, and with analyzing various machine learning model, we choose to have a model which is more useful for classification purpose, and how it is work for prediction purpose. Considering that, we choose this artificial neural network, random forest, and support vector machine. And sorry, same, the slide is not changed. Both of them are showing same. Okay, I'll explain that, but it didn't change. Support vector machines, it is working like decision trees. Multiple decision trees are framed to classify the informations, and artificial neural networks uses hidden layers as well as neurons. It exactly mimics a human, like human brain. So we, as much as data feed into the system, this will work nicely. So considering that, we feed a huge amount of data for that. And random forest, it is the main intention of random forest to identify the relation between the land surface temperature as well as the other additional parameter what you discussed, like BSI, NDMI, and NDVI. And so these are the results we obtained with reference to Kurvai and Samba. What you observed, this land surface temperature, of course high, it goes up to 34 degrees Celsius, and minimum temperature is 15, maximum temperature is 34. Also it affects the crop yield in the Kurvai season, but not in the Samba season. Why? Because the time is, the rainfall is more during that Samba season, so the land surface temperature, it's not influenced as like Kurvai season. And as per the challenge concern, in India, if you take other countries like USA or Europe, they are doing the cultivation for a larger area. For example, hectares of land, 1,000 acres of land. But here, many small holder, that means farmers, they have only less than 2 acres of land. So in that case, sometimes the productivity is not that much, and the farmers also not having the basic idea what are the things we supposed to follow as per this agricultural production concern. They don't get proper ideas what kind of the rotation should be required to improve or increase the cultivation. These are the other challenges are there, but still this land surface temperature also influencing the outcome. And this Kurvai seasons, as I mentioned, 34 degrees Celsius maximum and 15, and Samba is 32 degrees Celsius only, as far as this the year which I mentioned from 2001 to 2023. The 22 years, these are the differences what you observed. And these are some of the, I mentioned Kurvai, as I mentioned, 34 degree. The one indicate these are the locations having highest temperature as per the study concern, 34 degrees Celsius. So I have mentioned only the highest temperature area. This is for the Kurvai, and the next one is Samba, and second indicates where the highest temperature as per the Samba concern. The two indicates the location where is having higher temperature in the area during the Samba season. And now the third part, the results of land use land cover classes. And here we have both land use land cover, how much area agriculture cultivated. It is nearly more than 2,000 square kilometer area in Kurvai and Samba season, and how the land surface temperature with reference to the area, the land use land cover classes. Of course, the barren land, as far as the study concerned, the barren land have highest temperatures. If you have the water body, the temperature is less. Even for the agricultural land, the temperature is less. And this is how both are linking. How can for that we have combined these two the plot in the same diagram. The third one is about what we measured, what we calculated with the help of the ND software for land use land cover. if you look at the first one is talking about I think LST. I didn't see. Yeah. Okay. The first one is LST, land surface temperature. If you look at the build-up area, that is red in color. In the second is red in color, where the LST is high. So the build-up area is having more LST. Of course, we would know that due to the conversion of more pavements. So we cut down the trees, and there is less trees in the urban area, especially the country like India, more congested, so the more populated. Because of that, we started to cut the trees for the residential development. And the third one is about, I think, NDWI and the fair soil index, and NDVI, and last one is NDVI. So these are the various results what we obtained from the software, and these are related. For instance, if you look at what do you call bare soil index, it's very high as far as residential area concerned, and even you can take the barren land, you can find the bare soil index is more. So agricultural land, of course, you have better NDVI. So this is a good idea. I mean, for the better presentation we had, but it's small, but for the better presentation we had in the same plot. The left one is talking about Kurvai, and the right one is talking about the Samba season. And this is again whatever I discussed in the previous slides. This is a textual presentation, nothing more. And here bare soil index is positive, where you have more land surface temperature in the case of barren land. And NDMA is negative because moisture content will be more in agricultural land. NDVA also is negative because agricultural land have more what you call normalized difference vegetation index. And rainfall, if the rainfall is high, of course you have less what you call land surface temperature. This is all about how it is linking between these parameters and land surface temperature. And eventually we had the results from various models in which artificial neural network and random forest work better. Though support vector machines, it is good for linear and non-linear model. The results what we received from a support vector machine is not promising. And this diagram is showing for Kurvai for different models for the Kurvai season, and this one for Samba seasons. Now the thing is, we developed the model. These are matched with the statistical analysis. So we developed a correlation coefficient by using Pearson heat map to compare the outcome, and which we have better correlations for NDVI and rainfall, but LULC have less compared to other. It is very less. The left one is talking about Kurvai, and the right one is talking about. This is very important, how the correlations between the various parameters. So that is very important when you train the model. If the correlation is not, of course, a model machine learning will work for linear, non-linear data. But if the data is linear, that it is easy for them. So the system will understand better, so that training will be more effective. We can provide better outcome. Of course, we can choose the model based on the data what we have. But basically, it is better to have better to understand the relationship between the variable to feed the data into the system to have better outcome. And the student took the field verification also. Of course, it's done before and after the validation is carried out. Some of the field data which we observed from the study area. And this one about, as I mentioned, the validation is important. The land use land cover validation is carried out from the field, and this temperature is like matched with the weather station data, and Landsat temperature derived from LST collocations are matched with the weather station, what we observe from Indian weather stations. And this plot is talking about that. And it is somewhere it is not matching actually. For example, here there is a difference is there. But of course, we can increase the data sets in order to have a more reliable outcome. And there are limitations as per the study concern. We didn't take land surface temperature for night. And the second point is agricultural practices. Because farmers, of course, nowadays even educated Indians are started in the agriculture. They are doing organic farming. They are more interested. They are earning because they know idea how to improve the agriculture productivity, how the Israelis are farming, vertical activity, how they are improving the crop productions, the technology they adapted. For example, drone nowadays used for monitoring the stress of vegetations, healthy of vegetations, where the fertilizer is required. So these are all things are can be adapted, but the farmers are they are only laymen, but they need to have a better advertise. I mean, they can if they have very good recommendation from the government or other educated people, they also can improve. But these agriculture practices also can influence the final outcome. And eventually we conclude with various outcome. But what we observed, of course, land surface temperature is influencing, but with reference to the additional parameters. The study, what you done, carried out, the Kurve area got influence, but Samba didn't get affect. Maybe you include other parameters if it is possible. Maybe we come up with better outcome. So with this completed, and these are reference. And I'm very thankful for SRM IST for allowing me to go for it, and DAD for supporting me, and AGSE team, Professor Baer, Schroeder, and all the team. Thank you, and Colombia also for providing me this opportunity. Thank you very much.
Yeah, thank you for the talk. I don't know where the micro is. Someone has eaten up the micro? No? Okay. Anyway, there it is. Yeah, for time reasons, maybe just one or two questions. The floor is open for questions. Any questions? Yes.
Yeah, thank you for your presentation. Yeah, okay. I was wondering if you have sensors in the sensors in the fields that you have been investigating.
A sensor, you mean to say that for bare soil index and?
No. Like sensors in order to compare with the vegetation indexes that you have calculated.
Yeah, we have the spectroradiometer. We took the field for spectroradiometer for measure the spectral characteristics.
And there are differences or meaningful differences?
Of course, when you compare with satellite data, there is a difference. But the training samples, we try to match with this the satellite data. So those areas having better matching, we choose that actually. Because that is 30-meter resolution. This is field with higher resolutions. You have the variation always will be there. We took many samples with that best training samples we choose for the classifications.
Mm-hmm. Thank you.
There's one other question. Yeah, thank you.
Thank you so much for your presentation, sir. A lot of information. I'm curious about something. You use Landsat, right?
Yeah.
Do you think if you use a smaller spatial resolution will affect somehow your results?
Yeah, the thing is, you are right, it will affect, but the availability of data, that is very, that is the main point concern, because we are taking Kurve and Samba season. If you look at the data, 2001 Kurve season it is, and 2002 we took for Samba season. Mm-hmm. Because we consider here the availability of data. Of course, since it's a large scale, So this the resolution is not going to make much impact, because we are going to doing the calculation for 2,200 square kilometer, the whole regions, which consists of 9 blocks or something like that, in which, of course, if you go with the Sentinel and other case, we can get a better outcome, because that is having higher resolution outcome. But since we like to have the analysis from 2001 to 2023, that is the main reason we went with landscape data.
Okay.
That is absolutely right. There is a problem with, but since it covers large area, that is negligent. That's what I feel actually.
Okay, thank you so much.
Okay, then thanks again for your nice presentation. Then we will continue with the. Then we will continue with the next presentation. The next presenter is Nate Peña. I hope she is here. That's you? Okay. Unfortunately, I didn't receive any biographic information, so maybe you can introduce yourself just in some sentences. Okay. I just know that you are an alumni here from this university, but that's the only information you have, so maybe you can give a short introduction of yourself.
Muy buenos días. Una disculpa que voy a realizar la ponencia en español. Mi inglés no es muy bueno, pero espero entiendan muy bien toda la información. Ahí está, perfecto. Sí. Bueno, muchas gracias. Bueno, mi nombre es Saray Peña, Nejit Saray Peña. Soy ingeniera topográfica, estudiante de la maestría en Ciencias de la Información y las Comunicaciones de la Universidad Distrital con profundización en inteligencia artificial. El día de hoy voy a hablar sobre la estimación del vapor de agua troposférico a partir de señales GNSS, sus aplicaciones y beneficios de las estaciones CORS en la gestión ambiental y el desarrollo sostenible. Este proyecto surgió a raíz de un proyecto de pasantía desarrollado en la empresa Cuatro Conceptos en su semillero de investigación de desarrollo e innovación, y a partir de allí surgió como esta necesidad de encontrar de qué otra forma podemos aprovechar esta infraestructura ya existente de estaciones CORS tradicionalmente utilizadas en geodesia, y cómo sacarles un provecho en otro ámbito diferente a la ya comúnmente utilizada. Este es como el contenido de la presentación. Bueno, en cuanto al contexto, es importante iniciar con el tema de la troposfera. La troposfera, como ya sabemos, es una de las capas más bajas de la atmósfera, en la cual se desarrollan la mayoría de los fenómenos meteorológicos y contiene casi todo el vapor de agua de la atmósfera, ¿no? Este es un elemento clave para la formación de nubes y precipitaciones y es un regulador esencial del balance energético de la Tierra. Tradicionalmente, para medir el vapor de agua se utilizan radiosondas, satélites o estaciones meteorológicas, pero digamos que esta es una infraestructura que a la larga es costosa y no cubre como tal todas las regiones que podrían llegar a ser de interés para una comunidad en específico. Digamos que en este escenario surge como esa oportunidad de aprovechar esta red GNSS CORS, que es una infraestructura ya existente y que se encuentra en expansión, para obtener información continua sobre el vapor de agua troposférico, y pues esto sin necesidad de instalar equipos adicionales. Bueno, teniendo en cuenta esto, digamos que este trabajo busca evaluar como ese potencial de aprovechar las GNSS CORS para estimar el vapor de agua troposférico y de esta manera complementar los métodos meteorológicos convencionales. Esta oportunidad radica en que pues, Colombia cuenta con una red geodésica nacional magna eco bastante grande, administrada principalmente por el Instituto Geográfico Agustín Codazzi, y actualmente se encuentra en expansión con el fin de cubrir mayor territorio. Y digamos que a nivel internacional, esta técnica de la estimación del vapor de agua troposférico ha sido investigada y aplicada en varios países como Tailandia, Indonesia, Argentina, entre otros, y se ha comprobado que su uso es bastante eficiente. Digamos que pues nuestro objetivo no es como tal reemplazar la infraestructura ya existente meteorológica, sino más bien sumar una herramienta que, digamos que con la misma inversión que se está aplicando en esa ampliación de infraestructura geodésica, pueda ser aprovechada en otros ámbitos como el meteorológico. Bueno, digamos que el funcionamiento de las estaciones COR se podría resumir en estos 7 pasos. Inicialmente, una antena fija en terreno que generalmente se perfora y se instala con una varilla a una profundidad mínima de 5 metros, máxima de hasta 20 metros. Esta antena AR20 recibe señales satelitales, la cual lo convierte en datos precisos a través de su receptor GRS50. Esta información es transmitida por medio de un router industrial y un módem al Instituto Geográfico Agustín Codazzi, quien se encarga de validar la precisión de los datos recibida por los satélites, realiza una depuración de estos y posteriormente los publica en su plataforma Colombia en Mapas, la cual es una plataforma de acceso al público en general. Bueno, como lo mencioné anteriormente, estas antenas reciben señales satelitales. Sin embargo, cuando estas señales atraviesan la atmósfera para llegar a la antena AR20, sufren un pequeño retraso llamado retraso troposférico debido al componente de humedad y de moléculas secas en esta zona. Este retardo lo que hace es que la señal no llegue en el mismo tiempo en el que llegaría en caso de que estas moléculas no existieran, y a partir de esto se puede calcular cuánto se tardaría esta señal en llegar a la Tierra, comparando las condiciones óptimas en las que no existiera este retraso con las del retraso ya existente. Como les mencioné, este retraso se compone de 2 componentes, valga la redundancia, uno seco y uno húmedo. Este húmedo es el que contiene el vapor de agua troposférico, y este se traduce en lo que sería el contenido total de vapor en una columna de agua que se extiende desde la Tierra hasta la superficie. Bueno, en cuanto a lo que realizamos experimentalmente, se realizó a partir de los datos obtenidos de la estación Korskuma, ubicada en Kumariovich, una de las estaciones más recientes construidas dentro de esta densificación. A partir de allí, utilizando los datos RINEX, para una fecha en específico, una hora y minuto en específico del día, teniendo en cuenta que es como un desarrollo experimental, calculamos a través de la plataforma CRSP, una plataforma canadiense de acceso al público, que permite subir estos datos RINEX y nos arroja de vuelta todos los archivos como clave de este archivo, y uno específico relacionado con el componente meteorológico, un archivo .top. Este archivo nos permite obtener este componente húmedo, el cual a través de diversas fórmulas y teniendo en cuenta presión, temperatura, el contenido de agua de ese momento, nos permite calcular el vapor de agua troposférico. Este cálculo lo realizamos a través del lenguaje Python, aplicando estas fórmulas, obteniendo para Kumariovich un resultado de un 20.45 milímetros de vapor de agua precipitable en esa zona, lo cual digamos que es un valor consistente con las variables climáticas y la situación climática de ese territorio. Digamos que este valor aunque corresponde a un único momento del día, demuestra que es posible obtener estimaciones de vapor de agua troposférico en regiones sin necesidad como tal de una instrumentación meteorológica tradicional. La principal ventaja que podemos obtener de esto es que podemos contar con datos continuos que ya se toman, vale la redundancia, de manera continua todos los días, en todo momento, y esto permitiría analizar variaciones de áreas estacionales asociadas a eventos meteorológicos extremos. Digamos que aunque este es un primer paso experimental, la metodología es replicable y escalable a toda la red de estaciones CORS, y sus resultados podrían validarse frente a los resultados de referencia como obtenidos con radiosondas o satelitalmente. Este trabajo, como les mencioné inicialmente, se desarrolló en la empresa Cuatro Conceptos, una empresa actualmente reconocida por MinCiencias como una unidad de investigación. Esto nos refleja mucho la importancia de la participación interinstitucional entre empresas y universidades que permiten llegar a resultados como estos, de aproximaciones a nuevas investigaciones y nuevos aprovechamientos de las infraestructuras o los temas ya como manejados normalmente. A partir de este trabajo se desarrolló una cartilla informativa, la cual se desarrolló en un lenguaje bastante cercano para todas las comunidades, de manera tal que cualquier persona que se interese en este tema pueda entender cómo se puede llegar a este resultado. Esta cartilla tiene un resumen muy detallado paso a paso de cómo llegar al resultado que logramos experimentalmente, y pues de esta manera aquella persona que se interese en replicarlo nuevamente con otras estaciones lo pueda desarrollar. Y adicionalmente este material lo llevamos a las diferentes comunidades donde se instalaron estaciones CORS el año pasado, que fueron un total de 26 estaciones. Y pues digamos que fue un material bastante acogido por las comunidades, teniendo en cuenta que generalmente cuando se van a instalar estas estaciones no hay mucho conocimiento de qué provecho le puede sacar como tal la comunidad a estos datos diferente a los geodésicos. Y bueno, digamos que como conclusiones podemos decir que estas estaciones CORS para estimar el vapor de agua troposférico representan una alternativa viable de bajo costo para complementar las redes meteorológicas en Colombia. Y aunque digamos que en este caso presentamos un caso puntual, la metodología, como les mencionaba, es escalable y su integración con otros sistemas meteorológicos podría mejorar significativamente el monitoreo y el pronóstico climático. Y bueno, la idea es que digamos que dentro de los pasos a seguir con este primer acercamiento se logre llegar como a un análisis con mayor temporalidad, de más estaciones, incluso generar un sistema de monitoreo a partir solamente de los datos obtenidos de las estaciones CORS, y pues también como que se impulse esa colaboración institucional para que las entidades encargadas de todo este tema meteorológico se apropien de esta infraestructura y la incorporen dentro de sus procesos internos ya de manera permanente. Y bueno, esto sería todo. Muchas gracias.
Thank you for the presentation. Maybe we need some translation for the questions, if there are questions. Yeah, so it's open for questions. There's already one from Miguel. He can translate himself.
Okay. Thank you. Thank you very much for your presentation. Mi pregunta es, la idea es cuantificar la cantidad de vapor de agua en la troposfera con GPS, pero una vez que lo sabes, ¿se podría usar esa cantidad de vapor de agua para corregir la señal de GPS para que fuera más precisa o...?
No, en este caso es más el enfoque meteorológico. Generalmente...
Okay, I ask... okay. I ask whether, since they use GPS and the delay of the signal to quantify the amount of water in the troposphere, once you know this value, the problem could be reverted just to correct the signal of the GPS.
So that was the question.
Now we got the question.
Thank you. Okay.
Ok. Bueno, tradicionalmente este retardo troposférico es calculado precisamente para corregir y dar mayor precisión a las señales recibidas de los satélites. Digamos que eso ya como que está de alguna forma. En cuanto al tema meteorológico, pues solamente está como para la estimación del contenido de vapor de agua en ese momento, que nos permitiría pues conocer las precipitaciones, pero tradicionalmente para las señales sí se utiliza.
Perfect. Thank you. Yeah, the answer was okay. Do you want to do it? Okay.
Okay. Thank you. The delay in the calculations is using the GNSS signals. To correct satellite signals. However, can be estimated for water vapor. However, it is not clear how to use it to forecast the climate. So, yeah, I have one question.
Yes,
quick
question.
Yeah, please. What are the ¿cuáles son las aplicaciones prácticas de calcular este vapor de agua, digamos, para el cambio climático? My question is, what are the practical application of these calculations for climate change?
Excuse me, I have a question that it will help to answer your question.
Okay.
Okay. Could you puedes ir a donde está el código Python? Okay. My question is, this 20.45 millimeters is water vapor, and it is the same as evapotranspiration. Este 20.45 milímetros de vapor de agua es igual a lo que nosotros conocemos en meteorología como evapotranspiración.
Se traduce sí al contenido de humedad de ese instante en el lugar. Humedad. No.
Thank you very much. Now, the number 20.45 is not evapotranspiration, it's humidity.
Humidity. Yeah.
And
Okay.
therefore,
They are related, but not entirely directly. Yeah. Okay.
Question.
Real multicultural, multilinguals.
I am going to try to complement Miguel's question. The idea is to use this information to help the numerical models, the weather. It's not only the PWD, because the tropospheric delay is already estimated using the software, including the models that already exist. But how we can provide more data to explain some numerical weather. So that is the way we can help to the global change in the long time observation. But one of the most important thing that is necessary to establish in some stations some basic weather station in order to have how to know how the conditions in situ are. Because we are collecting the data through the ionosphere to the troposphere, but it's necessary to have in some station some weather station, basic weather station that with 4 variables basically. Está diciendo de que lo importante del PWD no solo para conocer un poquito ahí la parte atmosférica del agua, sino también cómo se provee información a los mejoramientos de los modelos numéricos. Y que es importante también en muchos casos, siendo que es necesario colocar estaciones meteorológicas básicas con unas 4 variables para conocer las condiciones in situ. Entonces, that's one thing that we are doing in Colombia. We have already established at least 20 stations, permanent core stations, with the basic weather station in order to prove how the results are obtained using the GNSS data. I think that I can complement the question. Okay, Miguel.
Last question, please.
Ok, muchísimas gracias por la presentación, está bastante interesante y lo bonito fue el hecho de usar una herramienta que no está directamente dirigida al fin que tuviste vos en tu investigación, eso me gustó mucho. So thank you so much for the research, for your presentation also, and something very interesting is to use a tool that you're not going, this is not for this specific goal, but then you achieve it, right? Mi pregunta, bien, práctica y sencilla creo, esto lo están o lo van a comparar con datos de satélites relacionados a precipitación o con datos de estaciones meteorológicas también de precipitación. My question is, you're going to compare this result with satellite data related to precipitation or maybe weather station related also with precipitation?
Bueno, digamos que el alcance de esta aproximación experimental no ha llegado a ese punto, pero sería ideal seguir profundizando mucho más en ello y realizar una comparación como tal de con diferentes métodos tradicionales.
So they are not yet doing so, but it will be ideal to take this type of project to compare all those variables, let's say. Thank you. Gracias.
Thank you. Now, really, last question.
Yeah, it's a very short question. Una pregunta. Mencionaste que ustedes hicieron el análisis en condiciones óptimas. ¿Las condiciones óptimas serían generales cuando no existe humedad o son condiciones óptimas en cada una de las ubicaciones de las estaciones? Porque hay veces que las condiciones óptimas o una condición de una estación en ciertas zonas van a ser distintas que las de otras zonas. Entonces, las humedades van a variar entre cada una de las estaciones. Entonces, la condición óptima es cero humedad o la condición óptima es de acuerdo a lo que normalmente ocurre en esa ubicación específica donde está la antena. I was asking if they say that they compare the amount of humidity in the atmosphere in perfect conditions. So my question is if the perfect conditions are zero humidity or depends on each of the locations of the antennas, because the antennas will be determined, the conditions on the environment will depend on where the antenna is located. In some areas it's more humid yearly long than other areas.
Bueno, digamos que esta es una de las ventajas de esta metodología y es que como tal no se necesita una condición específica climática para poder obtener este dato, ¿sí? En cualquiera de las zonas donde estén ubicadas estas antenas se puede obtener el dato independientemente de la condición climática del momento. No sé si eso responde a tu pregunta.
¿Puedes repetir la primera parte muy rápido, la idea principal, muy rápidamente? La idea...
Estimar vapor de agua a través de señales GNSS.
Sí, the water vapor can be estimated in any station independently of the location. So, no entendí, digamos, la parte, se puede obtener esa condición óptima o ideal del cálculo, que es la pregunta que le está haciendo.
Una disculpa, no entiendo muy bien referente a esa condición óptima de la obtención del resultado.
Lo bueno de esta metodología es que no requería características específicas porque la antena sí lo va a generar independientemente de las condiciones.
Okay, yeah, okay. It doesn't need specific characteristics of the location of the station. So it can be used independently of the characteristics. Yeah.
Okay, thank you. And thanks again for your presentation. Muchas gracias.
Gracias.
And then let me introduce our next presenter. The last one for the session, exactly, which is José Luis Gutierrez Ocio from Bolivia. He has a degree in civil engineering from San Andrés University in La Paz, and of course a master degree in photochemical and geoinformatics from Stuttgart University of Applied Sciences. As climate change adaptation consultant, he worked for public and private institutions in many projects contributing to increase resilience to the impacts of climate change. So the floor is yours.
Thank you very much. Good morning to everyone. Thank you, Professor Scholder, for your introduction. The topic of my presentation, the title of my presentation is Geoprocessing World Climate using Python. This is a picture of Potosí, the study area. Potosí is a mining and historical city of Bolivia. It was declared by UNESCO as a World Heritage. My presentation is dealing with meteorological information. Meteorological information is very important due to its use to stay safe through weather warmings and climate monitoring and climate research. Also, meteorological information is used to manage properly resource, especially water resource. Also, meteorological information is used to boost economy. That means in the fields where water is an important resource as agriculture and livestock, it's very important to have meteorological information. And the last use of meteorological information is to adapt to change, as climate change and environmental change. But where it comes meteorological information, the main point, the most reliable source of information, of meteorological information, are the ground-based stations. For that, I will compare the meteorological information that comes from a developed country, and I will use as an example Germany, and I will compare with the meteorological information from a developing country as Bolivia. First, let's speak a little bit about Germany. Germany has an area of 0.357 million square kilometers. In that space, they have 2,000 meteorological stations. As you can see, these yellow dots are meteorological information. If you see, they are well distributed around the territory. But let's speak a little bit about Bolivia. Bolivia has an area, a big area of almost 1.1 million square kilometers. In that area, they have 403 meteorological stations. And you can see, this is Bolivia, this is the map of Bolivia, and you can see this is not well distributed. They are concentrated especially in the main cities. Leaving some space don't have enough information. And it is not possible to interpolate because there are high distance, a lot of distance that don't allow us to possible interpolate. And for Germany, these 2,000 ground-based stations, according to the World Meteorological Organization, they comply with the standards. But what about Bolivia? Bolivia, they will need at least 1,200 more meteorological information. And it will be ideal if we have 11,000 meteorological stations. And remember, Bolivia only have 403 meteorological stations. Why we need so many stations, much more than Germany? There is not only because of the area, but because the landscape, the topography of Bolivia. Bolivia has different, there is no homogeneous topography. In this part of the country, we have highlands of 4,000 meters above sea level. Here we have a mountain chain with peaks more than 6,000 meters above sea level, and we have in this part of the country lowlands as 252 meters above sea level. For that kind of topography, we need so many stations. But there is no matter only the number and the meteorological station, also the historical records. Again, comparing a developing country with a developed country with a developed, we have that for developed country as Germany, they start to record meteorological information since 19th century. But for Bolivia, even today, we have not a complete record in these 403 meteorological stations. That is why we need to look for another kind of source of meteorological data. And also, it is important to mention the institutional capacity. In the developed country, they have meteorological service that provides a lot of information. You request them and they will give you the information that you request. But it's not the same for a developing country where the meteorological service is the institutional capacity is very weak, and therefore they will not provide with the required information. Therefore, we need to find source information for meteorology. Let's talk a little bit about the study objective. The objective of the study was to evaluate the strength and the direction of a relationship between two sources of historical monthly data. One is world climate, and the other is ground meteorological station data that comes from the Bolivian National Meteorological and Hydrological Service. The study area is the Potosí. This is a Google Earth picture of Potosí. This is Potosí. And Potosí, during the last decade, faced a severe drinking water shortage. The water comes from two basins. One is the San Ildefonso Basin, this one, and the other is from Caricari, the other basins. And therefore, if we don't have enough meteorological information, we could not develop an adaptation plan because the plan needs to be based in information. Let's talk about one of the source of information, world climate. World climate, this is an example of the maps that world climate provide. This is for precipitation for December 2005. World climate has a spatial resolution of 2.5 minutes. That means it's almost 21 square kilometers at the equator. It is a database of high-resolution global climate data. I didn't find any other. In the last presentation, there were a question, what to choose. We choose what is available. And for the developing country, we take what is available and check if it's served for our purpose or not. And we will see that world climate is a good source of information, and we use it at the end. Other important thing for developing country is the data is freely available. In world climate, it's available. The other is the historical monthly weather available is 1951 to 2024 for average minimum temperature, average maximum temperature, and the total precipitation. Having a good historical record is a big advantage that we don't have with Tsunami, as you will see later. Continuing to talking about WorldClimb, this is a snapshot from the WorldClimb website, and this goes to a link that you could download a zip file. This zip file contains only one of these contains 120 GeoT files for each month of the year for a 10-year period. That means it used 2.3 gigabytes of hard disk space. But for the last period, from 2020 to 2024, we only have not 10 years data, but less, and it is only 1.2 gigabytes. If we download all the data for precipitation from 1950 to 2024, we will have at the end 888 GeoT files. That is a lot of data, and we will use 19 gigabytes of hard disk space. Now I will talk about the other source of information, Tsunami. It comes from Tsunami. Tsunami is the National Meteorological and Hydrological Service. As any other meteorological service, it is responsible for monitoring weather and water resource, maintaining the national network of weather stations, and issuing alerts and advisory on meteorological and hydrological data. In order that you have an idea where the study area is, here is South America, and here is Bolivia in the middle, and here is Bolivia, and here is Potosí, and the study area is in this part. In this part, in the study area, Tsunami has 8 stations, ground stations, but we at the end only use 5 stations out of the 8 stations because 3 of them has no enough meteorological information. What is important to mention about Tsunami is they provide the data at no cost. We could download from the website of Tsunami. You can download the same parameters, meteorological parameters as WorldClimb, but the problem is that Tsunami only have this record, the historical record from 2000 and 2024. We are speaking about climate change, and at least we need at least 60 years period in order to have some comparison with the data. Working with 888 GeoT files is not so easy to do that with conventional GIS as QGIS or AGSE. Therefore, we need to develop a geoprocessing application. For that, I use Python as a programming language, and I use Python because it's object-oriented programming language, and using that paradigm is easily to maintain and update the application. And also because Python has a lot of support in the web, and also have a lot of libraries you can use. And I will talk of 2 mainly the libraries that I use in the application. One is GDAL and the other is Panda. GDAL is a geospatial data abstraction library, which is a computer software library for reading and writing raster and vector geospatial data formats. One of them is GeoT files. That means that we could process with GDAL the WorldClimb maps. GDAL is not new for all of us, I am sure. if you work with QGIS or if you work with ArcGIS, in the background you will use GDAL. And the other library is Panda. Panda means, for some people, panel library, or for other Python data analysis. It is an open source Python library that is used for manipulation and analysis, and that's why we use that information, that library, to work with tabular data. Usually meteorological data comes in the form of tabular data. And also the information of a GeoT file also have a component that is tabular. What was the structure of the geoprocessing application? It was divided in 4 components of 4 modules. The first module is the Tsunami data loader. For that, we in this module, we use as an input 9 Excel files from Tsunami data, from these 8 stations, and using Panda, we convert all of them in comma-separate value files, CSV files, because why we decide to use CSV file? Because it is possible afterwards to use in many other softwares like Excel, R, MATLAB, and many others. It's very common extension that you could use. In the second module, which is WordClimb data loader, we use as an input WordClimb data 2,664 GeoT files. Remember, I say that for each parameter, we work with 3 parameters. Each parameter is 888 GeoT files. For 3 of them is 2,664 GeoT files. But it was not a problem for GDAL to work with that high amount of GeoT files. We use a GDAL command that is called build BRT, which at the end will output 3 virtual data sets using GDAL that these 888 GeoT files is converted as a band in 1 GeoT file, virtual GeoT file. The third module is WordClimb to points. Once we have this information in bands, we use the Tsunami station coordinates of each of the meteorological stations to take out the information at that point of 880 bands. For that, we use GDAL, and the command was GDAL location info, and we use also Panda in order to convert all the information in a CSV file. At the end, the last module was WordClimb data evaluation, where the input was the first output of the first module and the output of the third module. And using Panda, we could possible to calculate the Pearson correlation coefficient, and it was saved in a CSV file. But what were the results? The output of the application present for each station the Pearson correlation coefficient for precipitation, for temperature, and for minimum temperature. We ran 2 batches, one for 5-year data in order to check the application is working properly, and after that we check that everything is working fine, we use the 24-year data in order to have the Pearson correlation coefficient. If you see here, for precipitation is a strong correlation as we expect. Also, it's not so good, but it is a strong correlation for maximum temperature, and for minimum temperature it's very strong, good correlation. That allows us to continue working with word climate data. If these Pearson correlation coefficients are very weak, therefore we need to avoid to work with word climate data. After that, we make some processing data using word climate data. We create a graphic for precipitation at Potosí Los Pinos station. We work with that station because it's the closest station. It's 7 kilometers far away from these two basins. As you could see here, the signal for precipitation is very unstable. Some years, this is annual precipitation. Some years is high, some other year is not. But the worst thing is the tendency is to go down. For mean temperature was calculated using the average of maximum temperature and minimum temperature. As you could see, the signal is not goes up and down, but the tendency is to increase the temperature. Combining both, it's not a good news for Potosí, because if the tendency for precipitation is going down and for the temperature is going down, we will have less water resource in the future for Potosí. After that, we calculate something that usually do for climate change adaptation project, and is calculating the anomalies. For that, we compare with the period from 1965 to 1994 for precipitation and for evapotranspiration. The mean precipitation for that period, for the base period, it was 364 millimeters. And as you could see, in the period from 1995 to 2024, there are positive and negative anomalies. To have positive anomalies is no problem. The problem is that 1/3 of the anomalies is negative. That means that we have some shortage of water in Potosí. There will not enough water in the basins to provide to Potosí. And what it was interesting that find for most of the negative anomaly coincide with some events of scarcity, water scarcity in Potosí. That gives us a view that we are doing a good job using anomalies. For evapotranspiration, we calculate using temperature to evapotranspiration using hard grips. The same, as you could see, most of the anomalies are positive. That means there are a high quantity of evaporation, and if you see this number, the evaporation for the base period is almost between 3 and 4 times the precipitation. Starting with bad news, because if you have a greater evaporation and low precipitation, we are in an arid condition, and the problem with water will be year to year around. And at the end, it was the reason that we need to prepare an adaptation plan in order to avoid to what you see in this picture. Thank you for your attention.
Thank you, Mr. Luis, for your presentation. The floor is open for questions. Are there any questions? Yes.
First of all, thank you very much for your nice presentation. I'm glad to see Potosí, like very beautiful city, and like the methods that you use to like adapt, like from the lack of monitoring stations to then use remote sensing is something like that is nice that all of us can use. I have a question like you mentioned 21 square kilometers resolution, something like this, in one of the of your slides.
Here we are not talking about the resolution. We are talking about source of data. All the behind pre-processing, our client use meteorological information coming from satellites, but we don't deal with that aspect. We only download the information and all the dirty job made by our client.
Okay,
not for us.
But
I only use the data.
Yes, but do you know what is the resolution that you use for?
The resolution, let me see what you are talking about. No. Yes, I talk. Take about the spatial resolution.
Yes.
The spatial resolution is 2.22 minutes. The
20. Okay. Thank you. Thank you so much.
Do the stakeholders know about these results, about your project?
Yes, we work with the municipality of Potosí and with the institution that provides the water to Potosí. But this is the first stage of the project. We need to work a little bit more. They need to combine this meteorological data with other sources of information in order to complete the whole scenario of what's going on in Potosí in order to make an adaptation plan.
Okay, thank you. Any other questions? I don't see for the moment. So thanks again for your presentation. So it was already a long morning session. So the good news is that there's a small change in the program. This means we will first have the coffee break now, and then the presentation of the sponsors. So half an hour of coffee break. So we will meet again here then in half an hour.
Las letras. Desactívalas.
Aquí no me lo
So, hello? 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 Yeah, now. Thank you. So I hope you have a nice break, a nice conversation with your colleagues. So we continue with the next part of this morning. We have two presentations from two sponsors. One is from the company Geosystems, from Karin Suarez. So, please.
So, good morning, everyone. I'm very appreciate the invitation to us. So, in advance, I apologize for my English. It's a little bit less, a little bit more. Yes, but so who we are? We are Geosystem Engineering. It's a company. We are located here in Colombia and Panama. We have been in the industry of the topographic and geomatics industry for at least 25 years. Yes, so we are providers of a lot of brands and some geographical brands. Topographical instrument brands like Trimble. We are only authorized dealers for Trimble in Colombia. That brand, Trimble, is our best, brand in the company. Yes, so we are very proud about it. To talk about a little bit of Geosystems, we talk about. We not care about just the device, just the equipment, just a GPS, a drone, and here you go and buy. Yes, we care about the solution. Yes, we have a lot of solutions in this environmental. So the first I want to talk about is Trimble RTX, like a topographic surveying solution, which allowed high precision without base course, Wi-Fi, post-processing, and anything like that. Yes, you just have to use one receiver with RTS subscription or correction services. Yes, this solution, yes, have different levels of precision, yes, or accuracy. We have the Trimble RTX center point. Center point allows the user to get 1 centimeter, 2, of precision and accuracy, not just in real time. We have been compared, yes, real time and post processing results, and have little bit differences differences like centimeter differences, not just for horizontal, for vertical component too. The RTX service is a worldwide coverage. You can have this precision with Trimble in all the world, every day, every time. Is our one of the most used products of the line because it's translated to productivity. Yes, before you have one base, one rover, and just take survey points with one equipment. Now you have two. Before you have some restrictions with radio, with N-trip. Now this is the past, yes. But RTX came to complement some of the surveying solutions. And we have more about software. Yes, I have been in all the presentations, a lot of data man engagement and analysis and software, and a lot of cool things maybe for this application. So with Trimble, and we are very proud about it. With Trimble, we have the best tools for the best hands. Yes, you have all the knowledge about it, but you can use the best tools. In this case, I want to talk about Trimble University Partnered program. With Trimble, we have a very special program to universities who allows to have access to all Trimble Business Center suite. And what is Trimble Business Center suite? Yes, Trimble Business Center is a complete software who allows GNSS, photogrammetric, volume calcul, GIS, piping, utilities, drilling. But with Trimble Business Center university program, all the universities, not just in Colombia, around the world, have the ability to access this entire suite, and you could search more about it on the official page of Trimble. You could have a lot of access to all the modules, with a perpetual license, yes, and have a low cost. If we compare that suite with a commercial customer, commercial is here, and educational is here. If we talk about cost, yes, but with Trimble have this special package. With Trimble Business Center is for a summary, it's a complete environmental to a lot of data entry. If we have drones, yes, works. If we have GNSS of different brands, works. If you have just total stations, works. Yes, if we can, if we want, convert all the information in GIS, in map analysis, in connection with GIS systems, Trimble allows, yes. But is more or less what we can do. It's important to mention here that Trimble Business Center suite includes US Master. Yes, I see some heads. Oh, yes, yeah, because US Master is very used in this ambit. So US Master is included in Trimble Business Center university program. So the best tools in the best hands. Yes, is like our universities. And I heard about it in some presentation that you have some trouble in the data man engagement. Yes, you need some disk, you need some NAS devices because you have a lot of data. Yes, and it's a lot. When we work with satellite images, we have a lot of data, yes. But for this case, no problem. Data sharing is no problem with Trimble Connect. Trimble Connect is a common environmental of data, yes. So we can connect the right people with the right information at the right moment. That is the goal of Trimble Connect. Yes, for Trimble Connect, that license comes with every single subscription of Trimble Business Center, Trimble Access, and other products of Trimble. Yes, what is the best of Trimble Connect? No limit for data storage, no limit for projects, and no limit for users. Yes, you have one administrator and have a common environmental to make right decisions using the same information, the right information. You don't have a map map day one. The same map, day two. The same map with some modifications, day three. Yes, with Trimble Connect, you have a common environmental of data to share with other users of the project. So at this point, we can see that Trimble-like company and Geosystem as dealers of Trimble, we have a solution. Yes, I'm very repetitive about it, but we have a solution. We have hardware, we have software, we have cloud, we have Trimble Connect is not just about cloud storage. Yes, it's about work. It's about complements work with every person in the project. Yes, and you maybe I don't know, but you can find that kind of solution in other brands. Yes, so it's a little bit of Trimble, and it's a little bit the offer that we have. And for finish, we have something more. Yes, we have Trimble Business Center. That is maybe our child. It's a very powerful software, but it's have topographic applications. Yes, for different sensors. But we have some software bigger. We have US Master. We have Info Suite, and we have Trimble Recognition. Yes, Trimble Recognition, allows to the users customize everything that you want to search in the images. Yes, so you have maybe a lot of data, some images very big, and you have the capability to search in all the data what do you want. Yes, it's very automatic, is more productive, and integrates some EI. You could integrate AI, and you can customize what do you want to search. And the same is for Trimble Business Center. For Trimble Business Center have module named Macros. Macros allows the users programming in Python and drop to Trimble Business Center. Yes, so we have a lot of tools in this, but you can customize too. So, okay. We appreciate your participation. I am very impressed with all the presentation. That is a lot of research, and I think there's more about the tools here, and everything I talk about is more about the tools. It's about the research. It's about take informed decisions around the correct data. So this is the core of all of this. So Thank you very much for your time, for your attendance, and for having us.
Yeah, thank you. Yeah, thank you for your presentation. We continue with the next sponsor. From Geosystem, no, what? Galileo. Where are she? Moment. Sí.
Hola, muy buenos días. Mi nombre es Nicole Molina. Hago parte de la compañía Galileo Instruments. Galileo Instruments es una compañía que nace en el 2010. Lleva 15 años en el mercado. Estamos a la vanguardia con tecnología de punta relacionada con la ingeniería topográfica, ingeniería civil, catastro, minería, seguridad y geomática, suministrando equipos y productos de servicio de alta calidad desde nuestras oficinas que están ubicadas en Bogotá, Medellín, Armenia, Panamá, Perú y próximamente en Estados Unidos. Nuestro equipo técnico está integrado por profesionales de las ciencias de la tierra, especialistas y líderes de nuevas tecnologías y gestiones del conocimiento. Somos distribuidores de marcas reconocidas como CHC NAP, Autel Robotics, Riegel, Wintra, DJ, Skyfen y demás. En nuestra página web encontramos una red Galinet donde tenemos servicio de... Bueno, Red Galinet es una red privada de estaciones GNS permanentes de operación continua corso, que pues tiene una precisión de 1 centímetro en un radio efectivo de 100 kilómetros. Actualmente tenemos 36 antenas en todo el país, aunque estamos en crecimiento, y pues esperamos que puedan acercarse a nuestro stand y conocer un poco más de Galileo Instruments. Muchas gracias.
She invites you to go to the stand and to visit the different, or to know about the different instruments. Good. Thank you for your presentation. So we continue with the next session. This is also a continuation from the previous session. So I would like to read here our next speaker, Michael Mutali. In this session, we have 4 presentations, but the last one, she's in Ghana. I contacted her 2 hours before, but she doesn't have internet connection right now. Maybe in 1 hour, she can contact me, and maybe we can have her presentation. But at the moment, we have the 3 speakers here in this room, and we will start with the presentation of Michael Mutali. The topic of the presentation is Gender Responsive Spatial Analysis of Climate Change, Impacts on Land Access and Use in Namibia Urban Areas. Michael Mutali is a geographic information system professional and lecturer with over 20 years of experience spanning academic, local government, and the mining sector. He specialized in remote sensing, geomatics, and photogrammetry. Michael holds a master in our university in Stuttgart, and he contributes in teaching geomatics-related courses at institutions including Copperbed University in Namibia. His current research focuses on gender-responsive spatial analysis of climate change impact on land use in informatics settlements. His practical experience includes also managing geographic information infrastructure at Lusaka City Council. And he was one of the pioneers, the integration of drone surveys and terrestrial remote sensing of mining, monitoring, and contribute to land administration projects in informal settlements. So, his presentation. No, this one. So, you have the stage. Oh, yeah.
All right. Good afternoon. Is it afternoon?
Yes.
Yes. Thank you for, it's 11:30. Good morning. Thank you for the opportunity to be here in Colombia. It's a great place to be. I'm excited. I'm thankful for the opportunity for those who have helped provided the means for us to be here, for the opportunity to share the presentation and the research that I'm doing. I changed the subject a bit. I'm more looking at the methodology. Okay, so I'm looking at spatial vulnerability assessment tools for climate resilient urban planning. So this is a mixed method GIS framework. Okay, I listed down there the institutions that are dear to me. The Copperbelt University, where I'm teaching currently, Namibia University of Science and Technology. I am very much connected there with my former university where I was teaching, and I did this research there. The NELGA and DAD were the funders of the research, and then the AGSE for the opportunity to present it here. Okay. What prompted me to do this research was basically issues to do when we're trying to see, in terms of assessing climate issues impacts on how people can access or use land. There are certain things that come to play. We do not have enough data. There's limited availability of fine-scale data, spatial data in rapid growing African cities, so we find a challenge there. So we need to find this data. We need to come up with this data. And also the spatial patterns, the complex spatial patterns that are in most of these unplanned settlements, it's not ideal for, it doesn't work using the normal way we do GIS, apply GIS. So the irregular settlement geometry and the absence of conventional administrative boundaries, it makes it difficult for us to apply the things exactly the way they are from the software. So we need to come up with some ways in which we can enhance it. Also, there's a limited integration, the disconnect between quantitative and spatial analysis and local contextual knowledge. So this is something that I found out after reading about this. And of course, we've seen urbanization in most of, a lot of people are migrating to the urban areas. The urban population in informal settlements is increasing. This is the case for Namibia as well. We see a 3.5% annual growth rate in Namibia or sub-Saharan Africa in terms of population. And then the climate vulnerability also compounds the problem. They are staying in places where they are prone to effects of climate change, because they're staying in places which are hilly, a lot of erosion. So whenever there's the issues impacted climate change, they're affected highly. Okay, so that I came up with a research gap from all this to say there's need for a context-appropriate and data-efficient vulnerability assessment tools that should integrate analysis, spatial analysis, and local knowledge systems. So that was really the main idea behind it. And to try this methodology, we came up with areas. We chose areas, 4 areas in Windhoek. These are, as shown on the map, Chumise, there's Kuriangaba, Hakana, and Havana. These are informal settlements. in their respective geographical areas. So Windhoek is a semi-arid climate. It is a rapid urban growth. We see a number of, the growth there is a bit, if you see the statistics, is going up. There also, we could get climate vulnerability challenges which are well documented. So we decided to do a research in that area. I used the students from the school faculty, 10 students who helped us to undertake a research. They did a survey, did a questionnaire, and this survey was done using imaging maps, using QGIS plugin, and then we went in the field and did it digitally on a smartphone. And they were, as they are conducting the survey, they pick positions as well for the points that they are conducting the survey for. So in total, we collected a sample of 290 household surveys, which were coordinated with GPS coordinates. And the process of doing this was as follows. Of course, we did a household survey, about 290 ground control points, which we picked with GPS, as I've mentioned earlier. And we wanted to pick a number of aspects which are related to climate, demographics, climate issues, impacts on climate, how they use the land, the barriers to land access. So there were a number of questions which were asked to the people that they found. And of course, we used the local people in Namibia so that if the medium of the questionnaire was English, but if we find people cannot speak English, we could be able to go into the local language so that we can capture as much information as possible. Later on, we had to do a special, get special data to complement some of this information so that we can plot it and see what is happening, and also get some key informant interviews with some key stakeholders from municipal officials, from the meteorological department, from the statistics agency, just also to give us some other insights. Yeah, and then some historical data as well, climate data. And then we did some spatial analysis. In the spatial analysis, we used hotspot, the JETIS ODG analysis, where we had to calculate and see where there are hotspots based on the information that we got. So this was adapted for this scenario where we had spatial weightings, multi-scale clustering, and hotspot identification finally. And in addition to that, also we developed an index, CCVI index, which was helping us to get some other parameters so that we could use it in comparison with the spatial analysis with the hotspots. And together we combine these two and be able to do a correlation to see what each of these is giving us. So I'll explain more on the two methods, the JETIS and the CCVI development. And then later on, we did some mixed method validation, picked a few points, and be able to validate the results that we got to see if we are getting the truth from this, okay? And at the end of it all, we get some outputs from there. Vulnerability maps, we get some, and then other information can be used for planning tools, for decision support. And then the framework also, it comes as a result of all that. Through all the methodology, builds up a framework which can be reused, and then the policy tools. This informs also the policy tools when they're making decisions. The spatial analysis, there's some key adaptations that were incorporated there, like the adaptive spatial weighting. So instead of just fixing the distances and the distance weights, we adapted it so that we could have context adaptive approaches. So we have different weights for different contexts. We also multi-scale analysis, so you do it at different scales, household, neighborhood, or settlement. So simultaneous detection of localized hotspots and broader vulnerability patterns across multiple scales. So those are some of the adaptations which we incorporated. Also, we also incorporated some other information where we could find it, like slope, elevation, drainage, that could also influence maybe the vulnerability transmission patterns. So these are other information that we could incorporate into that. And this helps us to make better decision to whatever result that we get, it's better represented. So it's an improved spatial analysis, gives us that capability, and gives us, it enhances the detection of the vulnerability patterns in complex informal settlements and environments. So this was a methodology that was applied. And then the second aspect was the vulnerability index, which also was created based on some indicators. There's exposure indicator, there's a sensitivity indicator, an adaptive capacity indicators, and local context. So all this information was taken from the survey where we were asking them questions and we get these results, and then from those we code them into indicators, and then we feed this into the software, and then we generate then a composite climate vulnerability index, and then plot it and see where it's really a hotspot, where we can identify hotspots, where we can see that these things are being, we see where the issues of vulnerability, hotspots or low, or the other places where there are no hotspots as such, okay? And so these were the four aspects, so they were equally weighted at 25% each, okay? And the formula is shown there. So this was another aspect that was an innovation, which you could bring in a local context component, so inclusion of informal settlement specific factors, and also validated towards the local conditions, okay? And then afterwards, we came up with some hotspots, so we were able to detect a number of high-risk locations, which about 55 high-risk locations in certain areas. I'll show the map on the next slide. In certain areas, so we could find the hotspots where we could maybe tell the decision makers to go and see and give some, if there are any things that needs to be sorted in those areas, probably there is no drainage, or which causes maybe people to report that it was flooding and stuff like that. So we find those hotspots, So we identified these high vulnerability hotspots in two areas, which gave us a 99% confidence level, flood-prone areas in Okuriangava, in the eastern part, and then another area in the northern central Ochomise for heat and erosion risks, okay? This was also another thing that we could see, and we were able to actually map this and show some of these locations, okay? Like in the parts here in Okuriangava and also in Ochomuise. So all those points are the points which were picked by the students. So these are the four areas, and then we're able to see, depending on the CCVI, okay? And then we're able to detect those. And this gave us some confidence to say, at least when we incorporate all this local knowledge from the people, we are able to also tell where the issues. They are the best people to tell us where the issues, and also using the science behind it, we're able to also show. And then this could be useful for the people to make decisions based on that. This led us to some innovations, that we could come up with. We already spoke about this, where we could adapt certain things, so we don't just accept them. We want to put context-aware, scenario-sensitive algorithms for irregular patterns, settlement patterns. This is something that we want to continue looking at, to refine it, and maybe even apply it in other areas. Okay, so this could be applied in other African urban contexts, but this was learned from Namibian perspective, but it could be applied in other areas. So we have also informal settlement factors, which we included, like tenure, security, service access patterns, and community organizations. knowledge about other things, like there are a number of factors that were incorporated. So all these were included in this methodology. And then the multi-scale integration also, and the mixed method validation. So these are aspects that we were trying to see. These are issues that we could replicate in other cities, and they are also data efficient. They're suitable for resource-constrained environments. You don't have to spend too much to get this information, and also it can be integrated with policy, compatible with existing planning systems. Okay. So I mentioned that the most important thing for us was really to see how can this be used in other areas. We are confident that we can replicate this in other areas, of course with more research, with more understanding, but this was just a first. In my research, I didn't find much in terms of what I was doing, in terms of the gender aspect, where you include the gender aspect, and this is something that can be further researched on. So there's minimal data requirements in this kind of, what we used was just the household survey data, where we picked points, GPS points, and we had basic GIS data sets that we could get from the municipalities, and topography, infrastructure, services like water, sewerage, all these can be gotten from there. We have standard climate environment data like temperature. All these can be incorporated into it, and then we have the software that we could use, ArcGIS or QGIS. These are common extensions that are available. There's no specialized software required. And also we know that optimal settlement sizes, it can be scaled up or also or smaller. So you can actually adapt it to the settlement as the size is. And also it's a multi-hazard capable. So you can apply it to areas where there's flood-prone areas or heat-exposed zones or complex multi-hazard environments. So it's flexible, can be operated in all those considerations. And then the infrastructure adaptable. There's minimal municipal services. Where there are minimal municipal services, it could be applied. And these are some of the things that we have in our areas where we had this. There's partial formal connections and the full spectrum of development levels. So this some of the things that planning, application, and policy integration for people who are making decisions, it could be useful for them. So it also can be adapted for climate integration with adaptation plans, the community integration. So people are also can be involved in the decision making. They are also incorporated. So it's not just the people at the office making decisions. You include the people because you want them to also participate. And also the policy development, it is evidence-based. So for planning purposes, regulations, this can be good. So we intend to share this with the municipal council once we publish this information, and then they can also use it for their further refining of policy and all that. Also, it can be used for monitoring and evaluation, so baseline measures, because we have something that we can now build on and develop further. So the framework has got a great impact and scalability. Of course, it can be scaled to other areas. It can be used, it can be replicable across similar environments for evidence-based climate adaptation planning. And it's compatible with existing municipal GIS systems and standard planning workflows. We believe this could be something we can adopt. Okay. And to conclude, some of the key contributions we believe this could bring is this issue of robust mixed method GIS framework. So it is comprehensive, vulnerability assessment approach. It's quite comprehensive, so you can mix, you can add as many things as you can that can improve it and further refine it. And then it can be integrated. It's an integrated spatial analysis, so we successfully combines the spatial analysis, the hotspot spatial analysis with composite vulnerability index development. I believe this is better for you to get a better result. And then it's a resource-efficient methodology, we believe. So it can be replicable and it's data efficient. And also the performance of the of the methodology also and the applicability demonstrates strong technical performance. Okay, the full results and everything is not shown here, but it is in another publication, so that's why I didn't include it here. So I'm just presenting the methodology. So that's why you can see most of the results here. The future research directions, I believe, could be longitudinal studies, because this was just a one-time study. So we could track this over time. That could be an interesting thing to see, how this changes over time, and what are the temporal analysis. So this is something we're thinking about. Also incorporating machine learning, which has been also talked about here. This is another opportunity for us to see the enhanced pattern recognition and predictive capabilities. And also real-time data integration. I think we also talked about this, where you have sensors in situ and then you can get data real-time. Okay. And then the comparative multi-city studies, where you can apply it to other cities, cross-validation and framework refinement across African cities. So we believe this is a contribution for us for this research, so that this could maybe be taken up and maybe more research can go into it. So it establishes a foundation for evidence-based climate adaptation planning across the African context. And thereby we want to see the gap being bridged between research and practice. Thank you very much. That was my presentation.
So now is for our audience. Do you have some questions?
Thank you very much for nice presentation. I have just one question regarding to the data acquisition. As you mentioned, you are using the emerging map as a QGIS plugin software. My question is that you mentioned also you are capturing the GPS coordinates.
Yes.
Are you using the accuracy from your device, like a tablet or like a cell phone, or connected GPS to your emerging map?
No. No, for this research, I think the accuracy is not that much a factor. So we're just using the accuracy that is coming from the device. Yeah, it could be about 3 meters within a plot. I mean, you are within a plot. So if you can just capture a position near the house, we want to just match the house to the respondent where they're captured, so that we could tell where, especially where the person was when they were being asked the question. Yeah.
Okay.
Yeah, so that we just know the location. So then the accuracy was not much a factor.
Okay.
Yeah.
Okay. It was my question, because it was interesting if you are using the GPS connected to the emerging map, but it's not that kind of this accuracy for your GPS point is not, this coordinate is not that kind of relevant for your application. Thanks.
Okay, thank you.
So, another question.
Thank you very much for a very good presentation. I would like, I would like to find out, because it was interesting to see how you are able to incorporate local context information on the CCVI calculation.
Okay.
I wanted just to know which type of data did you capture, which you're able to incorporate in that equation. Like, was it some numerical data? Was it, and how was it just processed? If it was maybe categorical, so that it can be incorporated into the equation. Thank you.
Yes. Yeah. So this was. It was just that when we are asking the questions, we had a number of questions, different aspects of the questions. Some speaking to the climate issues, impacts of climate issues on the people. Others to do with the impacts on the access to the land after the first certain climatic conditions. So this was categorical data. So afterwards, you take this data and then you record it you classify it like which one is the most important, or classify 1, 2, 3 if there are many, and then you record it and then you put it in your index. So then afterwards you have like one index, you multiply this and it gives you a value. Then you give it a value, and then that value determines whether it's important in terms of vulnerability or not. Then we had that value, which gives us the hotspots where there is a lot of vulnerability, based on what we got from the people. Yeah.
So another question? No. Yes, I have a question. Do you have access to some census populations data that you can compare some data from the institutions and your data that you collected?
Yeah, the census data is readily available from the Central Statistics Office, National Statistics Office. Yeah, but we have not yet validated that yet.
Okay.
Yes, yeah, in terms of that, what we got was just the people giving us that information. Yeah, but that's another aspect which could also be for further research to validate. Yeah. The only thing that we did was to check maybe the municipal services. Okay. Yeah, that the municipal currently service these areas. That was used. Yeah, so we overlaid that on the map and be able to tell in those hotspots how is the level of services available based on what we got from the municipal council.
Okay, yeah, great. Okay, thank you very much. So, applause. Another question?
Sorry.
Oh, sorry, I didn't.
Actually, it was not a question.
Sorry, I didn't see you.
No worries. Actually, it's not a question. It's just to add to what he said, because I'm also from the same area. Yeah. The census data, the recent census data, was not available at the time they were doing the research. So you have census data from 2011, but then of course from here onwards, it is now available, so they can still incorporate it. I just wanted to point that out. So.
Right. Okay. Thank you. Okay, we continue with our next speaker. Where is she? You? So, Professor Vitanash Primali Anuktikita. Sorry for my bad pronunciation. She is Dr. Primali Anukita, professor at the Department of Zoology and Environment Management, Faculty of Science, University of Kelandia, Sri Lanka. She served since July 28. She holds a PhD in agricultural science from the University of Hohenheim, also in Stuttgart, focuses on the development of cost-effective maintenance, free salt water management sensor for small-scale farmers and research. Her academic foundation includes dual master degrees in photogrammetry geoinformatics from Stuttgart University and agricultural engineering from the University of Peradeniya, complemented by the bachelor degree in agriculture with a specialization in agricultural engineering. So welcome. We can continue your presentation. This one.
Thank you, Angela. And I really want to thank especially our professors from Stuttgart and Professor Bear, who initiated this conference. That is really important for all of us as alumni. And I feel always, I tell it like a family when I come here. And it's really great. I really thankful for all professors, Professor Schroeder and Professor Paul, and all help us to get this DAD sponsorship, and these are really important for all of us to come here and present like this. And even our local organizers, Dr. William and all his team, I really would like to thank all of them. Okay, and this is my topic today. I'm going to present And this really initiated after having some group research from our university for this area, because this Kalpitiya Peninsula is, Sri Lanka is already the tourist destination. It is a very attractive place, but this region, the Kalpitiya, that is a peninsula, is one side is the lagoon and the other side is the open sea. And that is very special, and even the land of that area, that we use it for lot of intense agriculture, and like 40% vegetables coming from that area, and even the fishermen are living. And with that, our case studies, the students went there and they talked with the farmers, and they just did some research regarding their socio-economic situation in their lives. And there we found out, because they were complaining regarding the climatic change, they don't know it is climatic change, but they are giving some, like the floods and some dryness sometimes, and even the natural land usage is getting changing. And because of that, we plan our research, we should try to help them, and by having to study the land surface temperature study for that small area, and with the NDVI changes, the greenness. And with that, we try to assess the long-term trends in land surface temperature and normalized difference vegetation index in coastal ecosystems. A case study of Kalpitiya Peninsula. And this one is for the 30 years of period we considered, from 1994 to 2024. And especially this work has been done from one of our undergraduates. For this Kalpitiya project, we have a team like MSc students, PhD students, and it's a big project. This is a small part of that. And Mr. Sendeviratna, he did the most of the work for this project. And this is the content of my presentation. And as introduction, I will show you this the location, and that is the coastal ecosystem that is very highly dynamic and sensitive to both climate and anthropogenic drivers. And in Sri Lanka, rapid urban expansion, agricultural intensification, and deforestation that have altered land cover patterns and influencing ecosystems and microclimate and human health. And the Kalpitiya Peninsula is an ecologically significant yet vulnerable coastal region in northwestern Sri Lanka. You can see that area, and that is ecologically really like the ocean. It has the coral reefs, and at the same time seagrass beds, and a lot of blue carbon resources are there. In the land also, a lot of, as I told you, the agriculture, and there are many sand dunes there, and they are also especially ecologically significant are there, and there are like that many specialties in that region. And then as our plan, we had to land surface temperature, we consider it serves as a key indicator of the Earth's surface thermal dynamics. I think in the morning we heard from Kuruppu Sami's presentation about the LST calculations. And then we, NDVI we use, it also need for the LST, and as well as an indicator of vegetation health and density. And LST and NDVI are widely used for assessing environmental impacts of land cover changes on local climate patterns. There are many research has been done. And our objectives were to analyze multi-temporal Landsat images from 1994 to 2024 with a 10-year frequency. We just examine like 4 different images for decades. And that will examine the changes of NDVI, and LST in the area. And then we estimate the correlations between LST and NDVI for the past 30 years. And then after that, with our results, we recommend some strategies for the sustainable management and climatic adaptation in coastal environments. And this is the area, and as I told you, like land use, land cover, it consists with some urban areas, agricultural lands, coastal vegetation, mangroves, and the barren lands, sand dunes, and the shrimp farms, salt marshes, and residential areas. And the climate is normally, it is, we consider like a dry zone in Sri Lanka, and tropical monsoon is there. The rainfall is coming from the monsoon. And the temperature is normally maximum 31 and minimum 27 degrees of Celsius. And in that region, normally the daytime temperature is higher and the nighttime getting lower temperatures. And the annual rainfall is from 900 to 1,100 millimeters. And the data collection. And for the administrative boundaries, those shape files we were taken from the Survey Department, Sri Lanka. And the satellite images we have taken from the USGS Earth Explorer. The images were, because we used from 1994, we had to use Landsat 5, 8, and 9. And for the data analysis, we use ArcGIS. And the correlation analysis we done using our software. And that is the workflow of our methodology. And the Landsat images 5, 8, and 9 for the years 1994, 2004, and 2014, and 2024. And then these all 4 images we have taken and then used for the calculation of LST. And we derive different layers for the top of the atmosphere, and then the brightness temperatures, and then we take from the NDVI the emissivity, and then we combine them and take the LST map. And after that, we extract some random 300 points to do the correlation analysis from the NDVI as well as LST. And here just the Landsat images for 1994, 2004 we use Landsat 5, and Landsat 8 in 2014, Landsat 9 we used for 2024. And here the descriptions about the bands. And then this is for the Landsat 8 and 9, and you all are familiar with those. And these are the equations we used. I think you have seen it in the morning also. And the equations we use to get the final value of the LST in Celsius. And here we incorporate the NDVI derived vegetation proportion to get the emissivity. And here is the last layer, LST in Celsius. And with that, we came to our results, and there we just got the average values for these 300 points. We try to get the average values for the years. For 1994, LST was 28.03 and NDVI 0.178. And like that you can see from 1994 to 2024, each year, like in 10 years time, LST has grown up to 36.53 degrees Celsius. And NDVI, that changes are a little different. And here you can see this LST trend for the 4 year, that the 30 years difference. And it clearly shows the upward trend, and with the overall increase of 8.5 degrees Celsius. And that mainly we think about it and we search, and that influence intensified land use changes, rapid tourism related developments, and deforestation in the Kalpiti area. At the same time, geomorphology in the Kalpiti area that characterized by sandy bare lands, and that even it has agriculture, it is a sandy soil. And the thing is, the farmers has to frequent irrigation they have to practice. And then those related things can elevate LST. And that will compare to dense vegetation and even water-covered surfaces, as bare land absorb and retain heat more efficiently. And the climate-induced stress on coastal ecosystems also contributes to this increasing trend. And then when we see the NDVI, here you can see the first 2 years is like a 10-year difference. NDVI has been increased, and then from 2004 to 2014, drastic increase we can see, and then 2024, again it decreased. And this NDVI trend in Kalpiti showed reflecting the surface of the vegetation recovery or expansion. That may be due to agricultural expansion and reforestation activities. And by 2024, what happened to that area? And that decline up to 0.21, that indicates vegetation reduction, possibly due to increased human activities and the land conversion or climate-induced stress on coastal ecosystems. And there we try to, we saw that sometimes climate affect to the NDVI, the greenness, or greenness also can vice versa, can change the LST. And these are the maps we derived for the 4 years, 10-year gap. And then we did the correlation analysis. There the results shows that Spearman correlation for the LST and NDVI each study year. And that will negatively correlate and across all time points. And the 1994, and that shows little bit stronger correlation. And then it will weaken, but still that relationship is 0.11, and 2014 it's a little bit change again and strengthen again in 2024. And with that, we can recommend for these LST changes, while a moderate negative correlation in 1994 suggests that vegetation played a significant role in temperature regulation. The decreasing correlation implies that other factors such as land use modification, urban expansion, and soil moisture changes may increasingly influence LST patterns. And the spatial analysis further highlights that urbanized and deforested regions experience the most significant LST increases, reinforcing urban heat island effect, and the critical role of dense vegetation in temperature mitigations. As LST continues to rise, the implications for biodiversity, agriculture, and human settlements in the Kalpiti Peninsula become increasingly concerning. And as the conclusion of this study, that demonstrate a significant rise in LST alongside notable changes with NDVI of the peninsula over the past 3 decades, that is highlighting combining effect of the vegetation, urbanization, and the sandy surfaces on the local thermal dynamics. The weakening LST-NDV correlation indicates that non-vegetative factors are increasingly influence surface warmth. And that relationship is not so strong because of the NDVI is not like the green, not only green effect for that. And the implementing targeted reforestation, sand dune stabilization, and sustainable land use planning will be essential to mitigating further temperature increases and preserving coastal ecosystem resilience. Future research integrating higher resolution, cloud-free datasets, and additional climatic variables will enhance understanding and support informed climatic adaptation strategies. And in the morning we talk about the policies, how we can bring those things for the policies. And that also in Sri Lanka we really need. And with that we need to start some negotiations and even the discussions from the political people and administrative people, and how these places, how we can protect and how we can especially help the people who is living on these areas. And those are the major aspects of our project. And but there were some limitations with the cloud, and we had to get the very minimum cloud cover. It was not easy, the Landsat. And we couldn't go for Sentinel because of we starting from the 1994. And then the spatial resolution, maybe if we can improve, there can be some improvements. And other things, the temporal resolution. We just took the one image for year. And that makes like maybe in future we want to do like continually. The problem was the cloud. And that's why we couldn't do it, because in the in Sri Lanka we are getting long periods, very hard to get cloud-free images. And that also like to see the real the climatic changes for throughout the year. The temporal resolution was a bit difficult. Yeah, with that I would like to acknowledge our research fund from our university. They facilitate for us to do this research. And thank you very much.
Thank Vitanaji for your nice presentation. I will ask for question. Okay, 3 hands.
Thank you very much for a very good presentation and showing these issues of warming, especially in urban areas. And I concur with you on the recommendation, but I just want to maybe ask what could be done with regards to using imagery that is of high spatial resolution, because I think it will be very important so that local action can be taken to know maybe which specific areas or which specific individuals where the temperature is increasing, like in terms of how can they apply their land use planning within even a plot to ensure that the increase in temperature is reduced or moderated as we move in the future. Thank you.
Yeah, thank you. Yeah, I think it's good thing. With this course resolution, we can find it out where are the places. Then we can go with the higher resolutions to make the implementation. Thank you.
Yeah, I have a question. Thanks for the presentation. It was very interesting. I mean, 8 degrees, that is dramatical, the increase in the temperature. I'm just wondering, you have mentioned the limitations of using this LSD approach. Have you used also in situ weather station data to validate your temperature data?
Yeah, Professor, the problem is we don't have here any meteorological stations. That is the other big trouble. Yeah, but we try to use that weather data from the online climate and data, and that also we are doing for the real climatic change. We are going to do some models. For that we use that data. But for this study, I didn't get anything. Thank you.
So thank you so much for your presentation. It was very nice, and actually I feel motivated to somehow reply it in my area, because I live also in the agricultural coastal zone. You mentioned something about clouds, right?
Yes.
I face the same problem actually, because that's the behavior of the cloud pattern in my site. Did you try to make a mean in between several images just to avoid this numbers inside the NDVI, for example? You know that the clouds have very low NDVI. So if in my case, what I did was to make a mean with several images in 1 month, and then you have a much better number.
Okay.
Then you avoid those low values that make noise, because it's completely not related to bottom of the atmosphere, right?
Yeah.
So maybe you can,
Yeah,
this one can be considered.
Yeah, thank you. Yeah.
You're welcome.
What we did was we just got the image and we tried to clean up that using other images, like the same year and very closer one. We tried many different ways and got the best one. We improved the image. And
nice.
But anyway, that also good option.
Yeah, it's just mean or median, whatever, it would work, I think. Thank you.
Thank you.
The time for our last question.
Hey, thank you for the presentation. It was very interesting. I'm very new for the topic of LST. However, I was looking at your methodology, and I want to know more about the NDVI calculation, because I saw that you are using for LST, you are using top of atmosphere radians.
Yes.
However, for the NDVI, you are using, there is not, I have the which type of images are you using for calculate the NDVI?
The same image.
Radians.
Same image. Like LST and NDVI, we use same image to get those values.
Yeah, but the level of processing, because one of them is radians, top of atmosphere radians. So
the different bands.
Yeah, well, because in order for calculating or creating indices for they to be compared across the time, it's always better, I think, from my perspective, to use a surface reflectance, the surface reflectance image, in order to compare them across the time. But it's only just a very technical question, so we can take it outside of the.
Any suggestion from you? What do you suggest? I didn't get it.
Because surface reflectance it contains the atmospheric correction.
Yes.
So with that one, you can have a more reliable indices, a more reliable index value.
Yeah, that atmospheric correction also happening in these equations, because we do like first top of the atmosphere, and then we take the brightness temperature, and there we do some atmospheric corrections also. It included there. Yeah.
Thank
you. Okay.
Yeah, thank you. Yeah, it's impressive, 8 degrees. That I was very surprised, the differences. Yeah. Well, we continue with the next presentation from Caleb Siyab, Dr. Negusi. He's Environment and Geographic Science Engineering, University of Cape Town in South Africa, and also with the Master of Photogrammetry and Geoinformatics. He's coordinator of the Earth Observation and Satellite Application Research and Training Center, coordinated projects on climate change, geoinformation, technology, disaster risk reduction, and water resource management. He also has collaboration networks such as Euronet, the University of Göttingen, and the University of Huelva in Spain. So, please.
Good afternoon, everyone. My name is Caldas Negusi, coming from Namibia. Namibia University of Science and Technology. I'm a lecturer there. Today I'd like to share with you a collaborative project with University of Göttingen and the Namibia University of Science and Technology with this title, Modeling Future Stream Flow Under Climate and Land Use Scenarios in Lower Okavango River Basin. The collaborators for this paper was Dr. Daniel Wies and Professor Martin Kappas from Uni Göttingen. To begin, I'd like to set a global context, with interconnected challenges, environmental challenges of water scarcity, climate change, and food insecurity, which the world demands sustainable resource management. These challenges are especially evident in semi-arid and arid regions of sub-Saharan Africa. And in these regions, we have highly vulnerable communities living. Within this context, as you can see from the image here, Namibia, Botswana, and parts, to some extent, parts of southern Angola stand out as one of the driest countries in the region, frequently affected by drought and food insecurity, impacting livelihood and the economy. So our research focuses on the transboundary Okavango River Basin, which is a river basin that starts its flow from southern Angola, passes through the northeast semi-arid of Namibia, and finally dissipates in the northwest part of Botswana, where it's known as the Okavango Delta. And the Okavango Delta is one of the largest inland deltas in the world, which means that it doesn't reach the sea. And this supports a unique biodiversity and livelihood within these areas, such as agriculture and tourism. However, this precious resource is threatened by climate variability, increasing population, and adverse land use practices. So this work investigates this system in parts of Namibia and southern Angola, which is, we selected the most densely populated area within the lower Okavango River Basin. So as you can, sorry, I keep on turning around. As you can see, we, in the photo collage illustrated behind me, we have the different activities within along the Okavango River Basin, with livelihoods highly dependent on the river. Various activities take place, such as livestock farming, small-scale rain-fed agriculture, and also the area has certain challenges. It has a stress from climate vulnerability with drought devastating crops, and human-induced land degradation such as erosions occur quite a lot in this area. And there's also the growing economic activities within the area is the tourism sector and the rapid growth of urbanization. So with this in mind, we came up with an overall aim of our study to use the SWOT Plus model, the Soil and Water Assessment Tool model, driven by downscaled global climate models projections and land use, land cover scenarios to simulate future stream flow. So the first objective was to simulate future stream flow under climate change and land use scenarios. And the second one was to assess these changes of stream flow across future time periods between 2025, 2040, 2040, 2070, 2070, and 2100, relative to the historical baseline, of course. And this was done under two shared socioeconomic pathways of SSP2 4.5 and SSP 5 8.5 emission pathways. Yeah. Okay. This is just to generally illustrate. I know it's just a bit heavy to see it in one go. This basically illustrates the structure around this research, which basically integrates climate model, hydrological modeling, and land use change assessments. All feeding into the future projections of and scenario analysis. To achieve this, we collected diverse data sets such as CMIP6, global climate model, climate data, land use, land cover data, soil data, and topographic data sets. Yeah. Then we went on to configure. We went on to configure the SWOT model. Yeah. And do parameterization, calibration, and validation of the model to ensure reliable performance before running the final scenario simulations. So now this zooms into one of the parts of the previous flowchart that you've seen. To answer the question, what are the what are the projection impacts of future climate and LULC changes on stream flow? First, we used 3 different downscaled global climate models to account for a range of possible climate futures. To get the most reliable outlook, you never rely on just one model. Instead, we used a diverse ensemble from leading international centers, NORESM from Norway, GFTL from the US, and IPSL from France. And secondly, we also, so for each of these models, we run simulations under 2 different socioeconomic pathways. A middle of the road scenario, which is SSP2 4.5, and extreme high emission scenario, which is SSP5 8.5. Finally, all of these scenarios were projected across 3 future time periods, leading up to the end of the century. Okay, some of the findings will be illustrated from here onwards. Yeah. So to see model performance and the projected surface runoff, this chart, as you may see, illustrates that. On the middle of the road SSP2 4.5 scenario, the longest light blue is representing the baseline, historical baseline data and runoff, and then it goes on to 2040, 2070, and 2100 through to the end of century. So now looking at the chart, the first thing that strikes you is that runoff is basically, they all agree that runoff decreases, yeah, from the historical baseline. And then of course the high emission has also we see a trend is generally amplified from the SSP middle of the road SSP2. Yeah. So more reductions are expected at the end of the century. So the overall message is clear and consistent across the different scenarios. So the basin faces a future with significantly reduced surface runoff, posing a major threat to the water availability of the river basin. Now, here we see certain key findings. Yeah, we look at precipitation and streamflow changes in these key findings, which points to a significantly drier future for the region. The mirror plot on top, you see the precipitation with the bars, and at the bottom you see the river flow, the stream flow. And the most striking change that you see is that with a small drop of rainfall, there's a much larger drop in stream flow. Yeah, and I think this is basically shows us that the relationship of rainfall with stream flow is nonlinear. Yeah, you can see with precipitation basically has projected decrease between 5 to 20% by 2100, and stream flow has up to 60% drop by 2100. And this proves to us the dry gets drier paradigm by Jeong et al. Published in 2022. Further key findings shown in these maps are basically the change in water yield. So this is basically the amount of water contributed by a certain area within the watershed. The historical map on the left shows that water is generated across most parts of the study area, of the catchment. You see a mosaic of colors in blue, shades of blue, which are basically contributors to the river. And when you now look at the projected to 2100, it's a very dramatic change with only small pockets along the river basin, along the rivers are contributant, and all else falls below the threshold of 200. Yeah, that basically is pointing to a collapse in the entire ecosystem and wetlands being lost. Finally, we also look at projected impact of land use change itself. The map on the left shows the current land cover, a mosaic landscape, yeah, of representing natural vegetation, wetlands, bare land, and cropland. What is striking is by 2100, the projection on the left shows us that crop cover can go over 65% of the area. It almost completely replaces natural vegetation and also overtakes the vital wetlands along the river. This leads to a main conclusion for this section. We have a dangerous combined effect, the land degradation together with the climate-induced drying, which we have seen in the previous slides, basically create a threat to the entire river system. So this is the summary of the findings. So this was one of the first integrated assessment combining CMIP6 climate projections with land use change impacts for the lower Okavango. And we quantified a severe drying trend, confirming that the basin is highly vulnerable to these combined pressures. So, in conclusion, it is clear that there's a severe drying trend which is happening within the river basin, and which is significantly worsened by the expansion of cropland at the expense of natural vegetation and wetlands. Yeah? Therefore, it is important that we look for sustainable adaptation strategies. Such adaptation could be introduced such adaptations could potentially be introduced are drought-tolerant crops, which could potentially improve soil health and land degradation, yeah, and restore degradation in land. And this is what I will be discussing tomorrow in my other paper. So the land adaptation strategies that we have identified. And finally, this research provides evidence-based support for water management and transboundary cooperation, like the Okavango River Basin Commission, which all three countries are signatories of. Thank you very much, and if you have any questions, I'll...
Thank you, Caleb, for your great presentation and for sharing your research. So I have two questions, but I think the answers might be connected.
Okay.
So the first one is, why do you think the relationship between the runoff and the precipitation is not linear? And the second one is, how is that the projection until the end of at the end of the century for this area is to have most of the area covered by croplands? I mean, because is it a consequence of the climate, or is a human-induced decision?
Okay. Yeah. Okay. Let me start from this one. Yeah. So the change, basically, that's a projection. I mean, it's not a projection that I did. We used a data that was projected data. Yeah. That was available from Chen 2022, and basically they projected using the CMIP6, the Land Use Harmonization Project. Yeah, they projected that there will be increase in croplands within the area. Yeah, so we used that data basically to project stream flow based on that. Yeah. So I don't know if I answered your question. Mm-hmm. So basically, that is the projected land use land cover by 2100.
But it's due to the increase in the population density?
Yes,
or?
Increase because of population. That's one of the reasons. But it's not only that they look at. They look at with the change in economy and with the change. There are many different variables that they look at as part of the land use harmonization. And the land use harmonization project is actually goes side by side with the CMIP6 project as well. Yeah. So the CMIP6 project has actually endorsed the land use harmonization project as the major data, land use data, to be used for future projections. The first question was, again, repeat.
Why the runoff and precipitation are not linear?
Yeah. Okay. I mean, it's not basically with a small drop in rainfall is going to be a much bigger drop decline in stream flow. Yeah. So basically, it's not proportional. That's what I meant. Sorry. Yeah. It's not proportional change, because with what we saw was with between 5 to 20% decrease in rainfall, which showed over 60%, up to 60% fall in a decline in the river flow.
But the land and the soil conditions are constant, for example, because if you are now taking into account the land use change, of course, maybe these croplands are much more demanding on water, and then they don't allow runoff. Or
Again, repeat. Sorry, I didn't understand.
maybe this land use change
Is constant?
No, there's a change, so the croplands are taking this water.
Yes.
So they are not allowing runoff. Is maybe the reason?
The drop, that I'm not 100% sure, but the drop in stream flow potentially is many different reasons. It could be infiltration, it could be abstraction of water by the croplands. These are the assumptions you make, but we have to go a little bit deeper to understand this.
Okay. Thank you.
Thank you for your presentation. Can you go to the slides of results? I think around slide number 8. Yeah. Why there is this vast difference between the three model? Because I think 10 minus 40 around the 15 or something like 10 mm of difference in the runoff. Why? Is there any reason why the difference between the horizontal graph in GFDL ESM model and the IPESL model, the value of IM is different, quite, because in one you have the rainfall that is in the 20, while in another IPESL model there is around 8. That means the difference is going to 12.
I think the answer was actually his presentation this morning. You've seen that different models have various changes in degrees, for example, even in precipitation. What one model predicts is totally different to the other model. So GFDL predicts by 2100 rain will fall 53, by minus 53, while the other one is minus 67, yeah? So these are the different parameters that they use, and these are big differences that you see. But not only on climate models, but when you actually look at even current models of rainfall, for example, yeah, starting from CHIRPS data or ERA data and so on, there's big difference. So how did we select this model? We used literature review for Southern Africa. So the different empirical researchers that have done, they've used GFDL, IPSL, NOR-ESM, and some have also used MPI from Germany. But so basically, this is what we used, and we did try with MPI as well. But MPI had a very erratic outcome. Yeah. So all the different global climate models, their prediction is basically different. So that's why the fall of prediction in GFDL, the rainfall, is much different than the IPSL, and it's based on that. But then what we see is the general view, where we clearly see all of them from the baseline, they're falling, all of them. Okay. So that is what we take as a final. But of course, we don't know which one is correct, which one is not correct, and they use different ways to calculate this. Yeah.
And my another question is that does this resource include there is also the groundwater? Okay. Yeah.
Sorry.
There is also groundwater system, and does this research somehow link to groundwater or not? Because
I didn't use any groundwater data. What I used was basically 5 different data sets. So precipitation, temperature, high and low. So minimum, maximum, relative humidity, wind speed, and solar radiation. So these are the 5 data sets that I used for the model. But of course, there are ways to use also groundwater potentially, yeah.
So we see the dramatic scenarios. This is also, I think, very dramatic that in 2100 we don't have water for the population.
Yes.
And also with the presentation from Sri Lanka,
yes,
the increase of temperature.
Yes.
So therefore, our profession is very important because we are able to analyze different sources of data and make this analysis for the future, for the population, for the nature.
one limitation, maybe if I mention, I didn't include it, is the land use land cover data sets. Yeah. So some people will say, will the change be that much? You know, I mean, it's a question mark. Quite a lot of studies also do statistical projections for their specific data. We decided to try out this global 1 kilometer projection data that exists just for this study. Yeah.
Yeah, thank you very much for your various presentation. It was very great. Yeah, unfortunately, Nan, she couldn't connect to the internet. Tried to contact her, but she didn't answer. So we have time to lunch until 2. Yeah, enjoy the lunch and see you at 2 here.